Ça.
No, not.
Okay.
I'll have it connected.
We are going to start in a few minutes. I'll remind you that any question is going to be taken via Slido, so you can download the app and follow the link in the application to post your question, and I will go through the question after the talk in the 5-minute QA session.
So you'll have the last 5 minutes.
Yes. I will show you some signage as a timeout and the time until the 5 minutes. So you know that when I post game over, there are 5 minutes for Q&A.
Okay, so the game over is at the start.
Yes. Of course, if you need some more time, I can give you more time to talk, and then we'll have less time for questions.
I have some adapters.
Okay.
Very short and
Chiudi la porta, per favore. Chiudi la porta. Okay. Yes. Okay. Welcome to the first session of talk of this year's PyCon Italia, and today Spella Giacomelli will talk us about the great relationship between Django and HTMX. A big round of applause, please.
Hi, my name is Spella Giacomelli. A little fun fact about me, I think I'm the only person with this name in the world because it's Italian surname and it's a Slovenian name. It's spelled Sh, if you're interested. I'm a software engineer at Jackasoft, and I also author tutorials and courses at testdriven.io. One of the courses I authored is Django with HTMX and Tailwind. Tailwind is not important in this part, but that's why I'm here today, to show you how to combine Django with HTMX. I'm going to start with representation of HTMX. Then we'll see how to add HTMX to your Django application. And at the end, I'm going to tell you not everything is suitable for HTMX, and why not. So who here's like JavaScript? Raise your hands. OK, that's really not a lot of hands. Who here, maybe one of you 5, feels comfortable using JavaScript? OK, more or less the same hands. I never liked JavaScript. I actually worked as a front-end developer. I never got used to JavaScript. So a little bad news for those of you who didn't raise their hands. HTMX is not a replacement for a full-fledged front-end framework. But a little bad news of those 6 of you who raised their hands. We're not going to write any JavaScript in this. So HTMX is a library that allows direct server interaction with HTML. This means you don't have to leave the HTML file. You just need to add few attributes. And the request that is triggered, the response that is returned is pure HTML. That pure HTML is then put back into your HTML page without fully reloading as we're used from Django. I'm going to start with the simplest example possible, just so you can see how HTMX works. This is not really Django specific for now. I filmed all my, those are all screen recordings, so I don't need to switch between my PowerPoint presentation, code, and browser. So pay attention to the bottom here. Once the user clicks, the joke appears. And if you can check here, the response is directly HTML. And second, the initiator, as you can see, is HTMX. I hope you can see from up close. It's not very readable. But the initiator here is HTMX. So the browser always knows it comes from HTMX. And as you saw, it was just a piece of HTML, no JSON or something like that. This is the code that does what you just saw. Aside from the URL, which is pure Django, the 3 attributes all cover what we needed. hxget is the heart of HTMX. The hxget triggered the HTTP request to the random joke. hxswap means the inner HTML, so not the whole element, this div ID here with ID joke. Only this part, the content, will be updated by the response. The hxtarget is how we set which part of the HTML will be replaced. If we leave the hxtarget out, the buttons content would be replaced by the response in this case. The only part we really needed here is the hxget. The hxswap, which is inner HTML, is actually the default value. So it's here only so you can see what it does. If we would leave it out, the result will still be the same. Let's talk about HTMX attributes a little bit more. There's around 30 of them. Using those 4, you can cover most of what you need. As I said, the hxget is the main thing here. It's the heart of HTMX. You can replace it with hxpost, hxput, hxpatch, or hxdelete. Without one of those, there's no HTMX. You can't trigger anything. All the other attributes more or less change the default behavior. So hxdelete triggers a delete request. hxpost triggers a post request. The second attribute you'll probably use is hxtarget. The default value is this. You can also write this to be more explicit, but without setting the hxtarget, the element triggering the request would be replaced. Typical way is to use CSS selector with ID, as you saw. You can also trigger closest, find, or next and previous, which means ancestor, child, and sibling, all can be targeted. The third important is hxswap. As I mentioned, inner HTML is the default. That means the inner content will be replaced. Outer HTML makes means that everything will be replaced. So in case of the button would disappear and be replaced by the response. You can also target before or after begin. That means that right before the element or right at the start of the element, or before end, after end, right at the bottom of the element or after it ended. The fourth important one is HX trigger. Since the request is automatically triggered by the element's natural event, so a button click, a form submit, you won't always use it. But you can change the default behavior, so instead of the button click, you could send the request when the mouse is scrolling to the button. Or you can even use some HTMX-specific non-standard events. One of the most interesting is revealed. We'll see it in action later on, which means the request is triggered once the element is scrolled into the viewport. You can also set multiple events. For example, in a search box, you would likely want to respond to the key app and to the search event. Now, this is the first real example. I prepared 3. As before, this is a screen recording. This is the way click to edit. So once the user edits the forum, clicks the edit button, the forum appears. The edit is performed, the save is clicked, and it's back again replaced by the details. So if you check here, if you can see, here the HTML keeps changing from the forum to the detail. Now I'm going to show you, which is the HTML code that covers this part. Those 2 are the templates you need. They are both child templates. They have a joint parent template, which is not really important here, so I left it out. Let's focus on the HX attributes. So HX get, you already met it. You know that it triggers a GET request. The target, again, nothing special. The whole ID, the whole div with ID recipe. And the HX swap here is changed, so the whole recipe will be replaced by the forum on the right side. The forum has a HX put. I think you can explain it to yourself. It's a put request to, again, Django URL. The HX swap outer HTML, also nothing different. Maybe what we should focus on is HX target, which is on the right side, it's this. On the left side is ID recipe. That's because the element triggering request in the first example, it's much smaller than what we want to replace. The target on the right side is actually the same as the element triggering the request, so we want to replace exactly the same element as it was triggered the request from. Just for a quick idea, this is pure Django, so you can know that get and put are in this example in the same view. This is not necessary. Actually, it can be easier to understand how HTMX works with Fast API, because Django does so much magic for us that it can be confusing a little bit at the start, because get returns the form and the put processes the form. As far as HTMX is concerned, this could be made to entirely separate endpoints in entirely separate URLs. You have a lot of moving parts when you're trying to use HTMX with Django. So here's a graph so you can easier understand it. The top part is loaded by the browser. Recipe detail page, plain Django. The only important part up there is that recipe detail partial contains details which were taken out of the parent template, and they are then being put back in. That's so we can first have some setup. We replace a chunk of HTML code, and once we do something with it, we put the same chunk of the code back. This is almost the main thing of combining Django and HTMX. You take something out, you include it back directly as include, as you know you're used from Django, and then at some point, some other endpoint will call this template separately. Then once edit button is clicked, the HTML request is made to the get endpoint. This time the form template is returned. And once the user clicks the save button, the put request is made to the same URL. But this time the partial template of the detail is returned. And the user, for their view, is actually back to where they started. We know that we came back to this point from a very different road. This is also important to understand. You get the same look, but the way you get it, it's different. OK, the next example I prepared is the endless scroll. In this, you have 6 recipes, and once the user scrolls to the bottom of it, the next 6 are added. Pay attention, maybe we missed it. Maybe you saw the HTML text keep adding up. So we started with pagination. I'm going to show you now. You know the paginate by. The thing you maybe never saw before was the get template names. This is the way how Django finds out which template needs to be used. And it's not typical to override it. But here, another fact that is important, we know that HTMX made the request because it sends the HX request header each time. So using those 2 knowledges, we can change the template we select. OK, I wanted to show you the later part. We're going to see how the select works. So the if part, again, Django, for loop last, and object has next. That's because we're only interested in HX attributes to be added at the last recipe currently on the page. All the other recipes, normal div, nothing happens. HX target is, again, this. HX get, similar. You're going to see if you're going to use HTMX by yourself, you keep repeating the same patterns. And what's maybe more interesting is HX swap after end. I mentioned that before. This means that the new 6 recipes will be added after the last recipe on the page. So not inside the div that has ID this recipe, but after it. If we would use beforehand, the recipes would be loaded inside the last recipe. The revealed, I mentioned, this is a custom HTMX trigger, which triggers the request once the element, recipe in this case, is scrolled into the viewport. Again, I love those graphics. I think they're very good at explaining what's happening. What's interesting here is we only need a single view. We also only need 2 templates, both of which are used once the first time browser loads it. So the user gets the whole page. They scroll down. They encounter the element that has those HX attributes. And the GET request is triggered. The response are added after it. The user scrolls again. The process repeats. Since we added the if, for loop last, and next page, only the last page will be loaded, and the last page won't have those attributes. OK, so the third example I prepared is not so much about how to do something. I just wanted to show you what can be done using HTMX. This is a list of ingredients. You can filter through it. You can edit an ingredient. You can also add a new ingredient. And since cream doesn't belong in carbonara, don't kill me, you can also delete the ingredient. I put together this in about 30 minutes. Once you're used to it, you can be very fast with the HTMX. However, this has a lot of endpoints. On the left side, There are actions you can perform, so you can search. You can search for ingredient, edit ingredient, save ingredient you edited. You add a new ingredient, and you can delete the ingredient. Search has a single HTMX request, which is hexposed to recipe ingredient search. The search then is posted to the search ingredient partial, and the partial ingredients list is updated. Edit ingredient requires the get request to recipe ingredient update. The update ingredient is first called get, partial ingredient update is called, and when you save that ingredient, you go to the same Django view, but this time with a put request, and I think I dropped an arrow. So this time, I think I dropped the most interesting one. Wait a minute. Update ingredient. So yeah, once you make a put request, because the ingredient is now updated, the partial single ingredient is now returned. I mentioned this is the most interesting part, because the partial single ingredient is actually returned twice, 3 times if we also account for the one that is loaded by the browser. If you check, both add ingredient partial and update ingredient partial both return the updated or the newly added detail. This is why HTMX doesn't necessarily means I have one HTMX request, I have one template, and I have one view. This can be combined and can cause multiple things. So, because as you saw in the previous example, HTMX means a lot of templates, a lot of URLs, a lot of views, and a lot of tests, I wanted to quickly go how I structure things. This is not the only way to do it, but it's a good way. You can start from here. Maybe you can find something else, but what's important is you have your code well organized. Even when I was preparing the examples for this, I first started with, I don't know, need this, I'm just gonna put it everything, and I was lost in like 10 minutes. So it's important because there are so many, you structure your code. I based everything on the views. So you turn your views into the package. Don't forget to put all the views in the init file so you can use it the way you're used to. Then name all the views related to single page as you visit it in the browser, put it in a single view spy file, and name all the views so you know by the first glance if there's a page, so loaded by the browser, or partial loaded by HTMX. I love using class-based views, generic views, to cover the easier things, the ones that are appropriate. For example, the frame usually can be just template view. The tests closely follow the views, and what's important, you know which views belong to which tests. The templates can be put in the same file, but I put it in the same directories, so their names follow, the directory names follow the views. As you can see, I put the page or partial differently from the views at the beginning, so I can know from the first glance the top one is the page, what's loaded by the browser, and everything else are the partial templates. URLs, similarly, you don't need separate files. You just need to put them in different lists. So again, they closely follow the URL patterns. As I mentioned quickly through disadvantages of HTMX, it's not a silver bullet. As you saw, quite a simple list required 6 templates. This, in my experience, is more or less the most you can get. After that, it gets bloated. So it doesn't manipulate the DOM if it's not a request-response thing. You can't hide elements on the page. You can't animate them. It's just used as a server communication. Obviously, if you're expecting more than one client, so a mobile app, it's not useful. It doesn't hold state, so if you need some more complicated thing like a shopping list, you can't use it. Or if you expect heavy front end, that again, it gets bloated, you can't really use it. It's also kind of hard to decouple because you suit everything to it. So start with planning what you actually need. So some final notes, which didn't have any place anywhere else, but the top one can be really annoying if you don't know it. You need to add a CSRF token as you're used to Django and Forum. You can make a request from anywhere in the HTML, so you can put the CSRF as you're used to in the forum. The easiest way is to put it on the HTML body. So wherever you trigger your request from, button, forum, whatever, you can trigger it from wherever, you'll be covered. The examples I covered are actually quite similar to the ones that HTMX has on their website. It's not Django specific, but if you don't know where to start, it's a good idea to check those examples. They also have HTMX extensions. I don't think I mentioned the delete. There was this notice that the item was deleted that disappeared after a while. This is covered by the HTMX extension. You can't cover what's going on with the HTMX with PyTest. You need to use something front end. I used Cypress. It's kind of fun to use. If you don't know it, I just wanted to mention it. If you got the idea, but you don't know how to start with it, I wrote a course, as I mentioned at the beginning. It's on test-driven. If you're more interested in fast API than in Django, I'd like to mention that I also will have a fast API with HTMX course coming out. That's it from me. I think I was good at time.
Can you hear me? Yes, now it's working. It's working? Yes, it is. So we have four questions, and so we have, I think, plenty of time to answer them. First one is, have you ever had problems with caching, like Django that caches the HTMX response and just renders the partial template instead of a whole page, or vice versa?
No, I don't think so, but the truth is, I never worked with a bigger firm that uses HTMX. I just did a few of my own projects, which were not bloated, and as far as I know, until now, I didn't have the problems.
Okay. And have you ever had problems with OOB swaps? Okay,
yeah, I know what you're
swaps.
talking about. What kind of problems are you talking?
Like after the swap, the page scrolls in funny ways. Sometimes.
No, never, but you worked with HTMX. As I mentioned, you don't want to overcomplicate things. I never had that problem, but maybe if you had, there were too many things going on the page, and you should move to something more powerful. This is really wonderful code to improve things a little. I use it for, I don't know, when you send the message to us on the web page, the forum is replaced with the confirmation the message was sent. I'm working with React currently. This can't be done. If you need something more powerful, it's probably that.
And there are libraries like Django HTMX and Django template partials that help you deal with HTMX and Django. Do you have any opinions about them? Do you find them useful?
As I know, I don't know if it's maintained. I started using Django HTMX library, something like that. The Code Bytes guy did them or used them. But no, HTMX, you include HTMX by adding JS tag to the HTML. So whatever it does, I know it was, the part I showed you where the template is replaced. This was the part that was covered by this library, and this is replaceable by 3 lines of code. So because it's so simple, I don't think you're going to need additional libraries.
Thank you. And one last question. I think we will have some more time for, yeah, just another one. So there are the file structure seems a bit complex. Is it possible to abstract away in a generic Django library the most common HTMX uses, like infinite scrolling, etc.?
If we check the example with updating the details or adding new details, this is a very similar code, but reusing it would require a lot more complications than just adding 3 additional things. So again, as I mentioned before, I'm sorry, that's a one-trick pony. Those HTMX covers simple cases. Once you need extractions and complications, and I don't know what, you're probably going to be better with something more powerful. Once you start thinking big, and I want this, and I want this, you're going to have trouble using HTMX at some point later on.
And how does the responsiveness and user experience differ when using React and HTMX? Like, it's faster, it's simpler, it's slower?
As I mentioned, I think what's the most important difference here, HTMX doesn't hold state. So for example, I use Trello for shopping. I don't know what's happening with our stores, but you can't use mobile phone in our stores. It doesn't work. So HTMX here wouldn't be appropriate. I can use Trello because it's some front end, and everything I add or remove from the shopping list will be updated once I get out and get the internet. HTMX doesn't do that. So since it doesn't hold state, it always needs to wait for the server response, and after that, it uploads it. React is faster because, as far as I know, React usually first updates what you see, and then it handles the server.
And there are another question, but I think you just covered it. Is there any pattern for state management, even with limitation HTMX?
No, there's nothing. The only manipulation you can do, you can display just a chunk of HTML and instead of the whole response.
And one last question from Slido. Are there security concerns with using HTMX, especially injecting malicious code? Any specific regarding security we should
I think Django with CSRF token should cover at least big part of this. I was wondering myself this because I put the code, the CSRF on body, but I don't think that should be anything. But again, if you need a very powerful, very secure, you're gonna need something else. I don't want to put you off using HTML. It's a wonderful tool, but it's a tool. If you need something complicated at the front end, probably not the right answer. But it's a great tool for your websites, your own projects. I'm preparing an example. We're starting to talk with the client about their requirements. And I have I want this, okay, maybe I want this. I'm going to use HTMX for this. Probably at the end, when the full project will be developed, it will be something else. But HTML feels comfortable, it's fast, and I'm going to start with HTMX. Once they break their toy and they decide what actually they want, I'm going to use something strong.
Thank you so much. And please. Thank you for your time. Next on stage, Yash about boosting Python web apps performance with Celery and Concurrency in 10 minutes.
I think I'm unsuccessful turning it off.
about Celery and how it can help our building our websites. A big round of applause, please.
Thank you so much. Ciao, I guess. So this is my first time speaking at a conference, so yeah, please be easy on me. But yeah, so my talk is surrounding how we can use Celery and use the concepts of concurrency and parallelism together to really improve and scale and build better infrastructure for your backends. So about me, I think I'm wearing the exact same T-shirt. Yeah. So yes. So my name is Yash. I come from India. I'm currently working as a backend engineer for a startup named Yasi, and I work with Django a lot. So I'm an individual member at Django Software Foundation. I contribute to the Django code base. I'm also a Django North Star Space Fellow. So yeah, that's great. Apart from this, enough of me. Yeah. So I love attending conferences and meetups. This is my first international conferences, but I've spoken at local meetups earlier. So yes, we'll get straight to the point. So what's your web framework meant for? This is usually confused with the beginners. So usually, your web framework is meant to handle all the business logic, all the Pythonic code. I'll say Pythonic code because it's a Python conference. So you can handle all the business logic, connections with the database, the queries, working with your APIs. No, basically the logic, business logic where you work with the frameworks. You don't give it your heavy or bulky tasks. Okay, it's not meant for that to handle that. It's just handle your request, pass data, pass request. That's what it's meant for. Again, not meant for. It's not meant for, I'll add some examples. So it's not meant for heavy, bulky tasks. So for example, you cannot add the ML-related code inside your backend code. Or you cannot add code for sending 20,000 plus emails inside your backend application. That's common sense. But for this, I recently, so the major idea comes for a project for this. This was a project I was building. It's illegal, so I didn't deploy it. So what I was doing was I was scraping a lot of news websites, okay? And I was scraping their data, and I was bringing them to an API endpoint. But the thing was, it was very slow, because news changed very rapidly, and I really needed something to fast things up. So that's why I stumbled upon Celery. So coming back, yeah, so Celery, as the definition says, Celery is an asynchronous task queue. In simple terms, it's a FIFO. It follows the FIFO approach. So for example, you have 5 functions, okay? Inside you have 5 Python functions, and you have specified you're passing these 5 functions inside a queue. So task 1 goes, task 2 goes, task 3 goes, and happens in a queue. So all these tasks are performed one by one. So this is the approach which basically Celery follows, FIFO. I mean, if you don't skip classes like me, you must know what is a FIFO, first in, first out. I don't do classes. So with Celery, we need a third-party softwares like RabbitMQ or Redis. So these are the brokers. So I told you about this FIFO, the queue. So the queue is used like basically with RabbitMQ, or you can go with Redis. It's your choice, but I use Redis. Oh, that was a joke, which but I will still do that. So I think from my shirt, it's pretty visible which framework I will use it as example. No, it's not Flask. I failed that, but yeah. So the architecture was like, basically I was using Django. So it was scraping, it was using the request library. It was scraping everything. I was using Beautiful Soup. It was bringing the HTML. It was passing it to the Celery beat. So Celery has 2 things, Celery workers and Celery beat. So whenever you want to schedule something, for example, it's 11:50 right now. You want to perform some task at 12 p.m. So you schedule your task with the help of Celery beat, this yellow thing. So this is a server in itself. So as soon as 12 a.m. hits, the Celery beat will start and take all the functions which you specified inside the code base. It will send all of them to the Redis queue, okay, one by one. So that's how. So all wait, the network is pretty bad. Yeah. So now Celery beat will take all those tasks, all the functions you define to be done inside the queue. It will pass this inside, and then it will pass it to the broker which I talked about, the RabbitMQ or Redis. I'm using Redis, so it passes all the tasks to the Redis, and then it sends it to the Celery worker, We'll get to the part later, but yeah, when you work with Django, you use these libraries, Celery, Celery Beat. Celery Beat was for scheduling the task. And Celery Beat results for managing the database of site, like this task performed at this time, and etc. Like, or it saves and tracks with the database, basically. So Celery uses a lot of, the main power of Celery is that it uses like you have a control over the concurrency and parallelism. That's the main, yeah. So on your laptop, usually, whenever you buy a PC, there are something cores. Whenever you buy, you must have won an octa-core or 8-core system, OK? So Celery leverages this thing. So usually, when you have 8 cores, for example, my laptop has 8 cores. OK, so 8 cores, I have an Intel processor, actually. So Intel uses something called hyperthreading. Or if you're an AMD guy, you must be using something called SMT, simultaneous threading, something like that. It's called SMT. So what it does, it divides your cores. So I have 8 cores, OK? So it divides each core into 2 threads, OK? And now you have 16 virtual cores. We say, whenever you go, wait, can I show that? Yeah, so there are 16. You can see 15, right? Like at the top. I hope you can see there's 11, there's 15, you can see. So I have only 8 cores, but I can see at the top, like if it's not visible, the cursor where there's, is it visible? Yeah, so there are 15, right? So it starts from 0. So that's why it's showing 15. So I have this many virtual cores in my laptop. I have 8 cores, but logical processors are a total different thing. If you're a Windows person, you can go to your control panel, I guess, and task manager, and you can see the amount of logical processors. It will show you the, yes, sorry. Network issues. Yeah, so 8-core means 16 virtual cores. And there are 2 options with Celery. Either you can use a core independently. And when I say core, I will mean virtual cores. Because at Pythonic level, so there are threading modules in Python, multiprocessing modules in Python, right? So they use they interact with the virtual cores. They don't interact directly with the, the system 8 cores. They will work with the 16 cores, which is visible. So Python will, so Celery has 2 approaches. One is process, and one is threads. So process, you use, so each virtual core has its own memory, has its own resources from the system, L1, L2 caches, and a lot of stuff. So they can use, so if you give a task to a process, that process will use the whole resources just for that one function performing the task. But if you give it to threads, it will share the resources. So that's our 2 approaches with Celery. I will come to this more. So no need to do this. So in the diagram earlier, we must have seen there was this thing called Celery worker. OK? What it does is, so Celery follows this law of master and slave. OK? So there will be one worker. And it will give, so for all the tasks which we had earlier in this. So for example, we have 6 tasks here. OK? So from the queue, all these tasks from Redis goes to the Celery worker. And then from Celery worker, it redistributes. For example, in the CLI command, I will come to that later also, you have said the concurrency is 6. So 6 workers have been spawned. 6 slaves, actually. So the worker will give all these tasks to, you take one, you take one, you take one, you take one. So it's distributed. So now at one time, you're doing 6 different tasks, and you are storing it in your database, the web scraping scripts. I'm saving that inside a Postgres, right? So at one time earlier, it was just synchronous. I was just doing one by one, one by one, one by one. But now it's asynchronously working. So at one time, it depends on your laptop and system. So at one time, I can do 6 scripts, and which makes it more faster because news APIs need to be put really fast. So that's how it works. So there are options. You can use either processes or you can use threads. It depends, actually. You use processes when you want to use, you want to do compute level work. So you are running ML models or compute something. So you use processes then. But if you're doing a task like IO bound, OK, so you should go with threads. That's better system designing. So as I said, workers is basically all the tasks is taken from the queue. The worker assigns them to either thread, whatever you have chosen, and there are different processes. So worker is basically the master. Now, on the CLI, we have pool. So these are basically CLI commands. Whenever you start the server of the Celery, you can pass like parameters to this. I will come to this. I will show you the live demo, actually. Yeah, a lot of people told me I shouldn't do a live demo because this always gets ruined. So these are some commands. Pool, concurrency. So I'll explain them once. I think there's a demo line. So yeah, so for example, this is a program, this is a CLI command to start the server, your project name and stuff. So pool here means either you want to use threads. So for example, you are calling different, you have 5 functions, and you're calling different APIs. Okay, so you must go with threads because it's IO one task. You don't need heavy compute. One core is sufficient to do that. So pool, in pool, you can either put, so prefork means, in Pythonic language, prefork means you will use as many cores, like the amount of cores is available on your system. You will all these cores. So either you can do -- pool is equals to prefork, or you can do -- pool is equals to threads. So that when you select threads, it will start using IO bound, for IO bound tasks, it will start using threads. But for now, for prefork, it starts using the whole processes, which I told you about. So, but then concurrency. So suppose I have 16 virtual cores. Okay, so I can tell, where was the command? Yeah, so now I can specify, for example, threads also. I mean, it's a limitation to Python that because of the global interpreter lock, we cannot make more than one thread work at once. But still, you have options to switch over threads. So if you're choosing pool is equals to prefork, so means all the 16 virtual cores are working. So now if you use concurrency equals to 5, so 5 cores will be working. Only 5 cores will. So you can, you have the control over how much asynchronous task you want to do. So this is actually parallelism in simple sense. So concurrency is equals to 5, so 5 cores will come, and those 5, so instead of in the diagram, I guess, network issues. So for example, here was 6. If I do the concurrency 6, the process will spawn 6 cores, but for 5, it will just spawn 5. So yeah, that's working with concurrency. And there's one more parameter called autoscale. I think this is one of the best things about this Celery. So this is a syntax -autoscale is equals to 10,3. So for example, I have 16 virtual cores. Okay, you don't know at what point, like at some times you want to you want to have an optimal solution. For example, I'm scraping something, and at one instance, I was requiring a lot of compute. So I was requiring 10 cores. Okay, but after some time, you don't need the 10 cores. You just need 3 cores. Okay, but those 7 are still spawned, and it's wasting space. So what autoscale does it? According to the work which you have provided, the function you have provided inside the queue, it will establish. So when it needs 10, it will just scale up to 10. And when it has no need, it just need 3. So it will just bring all the cores to 3. So other processes are free now. So yeah, that's a really good feature. Again, prefork means you want to use all the cores. Solo means the Celery worker, which was the master, he will do the work. Threads again. When you use threads, only one core is spawned. And in Python, what usually happens is not like usually in other languages. Wait, I'm not sure. But yeah, in Python, what happens is when there's one core and you are running a thread. So this is not just specific to one thread. So if core 1 is inside core 1, there's one thread going on, it can jump to another core and perform the other thread work. So it's not limited to that one specific core. The thread jumps from different cores in the Pythonic way. So yeah, threads, it spawns threads, and event is not the, I've not played much, but these are basically green threads. We'll not cover this. So yeah, again, I've just added the CLI commands, and I'll show you the live demo, like how things work. So prefork, I want to use concurrencies. By default, if you just run this much Celery to worker info, it will spawn all the processes available, like the max. So I have 16. It will spawn all the 16 cores if you don't specify all of this. But you should. So solo, again, you can see. So for example, I just didn't specify any. I just run the server. You can see there are 16 Celery working at my Linux. So 16, but when I use thread, okay, so there would be 17. One is the master, which allocates the task. That is also in itself a different process. So there are 17, 16 of them are cores, and one is the master. Here you can see Celery are 2. So one is the master, and one is the one core working, the thread, the IO bound task. So yeah, again, it's not the covers. Again, why to use Celery? Because I think it's clear with the whole asynchronous point of view, you can scale your backend, you can do things fast for a lot of other purposes. So high CPU intensive tasks, third-party API calls. One of those examples you can say, for example, of user comes. I'm just taking an example. It's not the best example, but a user comes onto your platform, okay, and your service provides that you'll provide an Excel sheet of all the emails, and you can send one email message to all those emails in the email sheet. Now, the normal how we plan design software is user onboards on the platform, he signs up, he comes and he gives all the emails, and he gives a message like, I want to send these messages to these emails. Okay. Now, when the user clicks on start, you don't want your backend framework to keep using that. You want this to be a total different thing, so that in the meantime, the user can come on the platform and visit other features of your website. So this is also like how to improve your UX. So you have just the user created start, and now in the background, you have given all the work to Celery, which is totally different from your backend framework. Okay, now all the work is with Celery. Celery is processing everything, and he is doing in the background task, and you can say, go see the website, your process will be done in 10 minutes, or something like that. So that's where Celery comes into the use. And some commands. Let's do the live demo, the most stressful part. It's working. So these were some scripts. And this is the whole project, the illegal project I told you about. I couldn't deploy this because probably I will be in jail instead of being here. But yeah. So I'll start my server. Yeah. So the time right now is, my laptop is still in IST, so I will just, please forgive me for this. So in Celery, I can just specify the time. So I told you about the Celery beat, the scheduler, right? Which schedules the time. So here's the, this is the syntactical part. So right now it's 3:34. I will just change let's do 3:35. Okay. And Celery minus A, news. OK, it's already, let's do 36, actually. News, beat, L, and 4. OK, no, let's do this. OK, 36. So this is the Celery beat server which we start. And then we have the worker. So this server which we started. I will get the screen bigger. So this worker is the Celery beat server. So this is the scheduler, okay? And this is basically the worker which was assigning the task. So Celery minus A news beat. Worker minus L and 4. OK, so it will start. Yeah, it started. It has some problems. So you can just see, this is without using Celery. OK, it's just like using it synchronously. So you can see the speed. It's OK, one by one. It's handling the task one by one. So one script got done, another script got done. Please notice the speed, because that's the biggest thing about the live demo. You can see it's very laggy. It's very slow. And you need to really be fast with the whole. So yeah, you can see this is synchronously, this is very slow. So what I will do is, now I'll show you guys how it works after using Celery. Yes. What is the time? 37. Let's do this right now. Let's see what happens. Let's see. OK, we are past the time. We need to start this again. I guess we'll have to wait till 38. How are you guys doing? Yeah, I just hope this works, or I will shoot myself. Oh, OK. OK. So I will do this 39. Don't worry, guys. I have a backup for this. I knew something could happen. But I will try. Like, I would love to show you the live. OK, it's good that I had a backup. So this is with Celery. Like, I recorded this just last night. I don't know why it's not working. So the schedule starts. Now just notice the speed. Yes. So now, so I didn't record the full video because already I don't have time. But yeah, so usually that process was taking around 7 to 8 minutes, 10 minutes, which is too much for a news API to be available on an endpoint. But with this, it was done within 31 seconds or something, which is, I think, doable. But we can more optimize this always. So if we go to this, so API endpoints. So now data is available on the API endpoints from the Django server. So I think, did you guys find it cool? Was it interesting? Yes, so yeah, I guess we are done with this. Thank you so much. This was my first time. Thank you so much.
Can we hear? Yes. OK. We have quite a few questions.
Yeah.
And I hope we will be able to go through them all. Come on, Slido. And how is Celery different from async.io? Is the FIO for you similar to the event loop?
OK. So async.io usually is single-threaded. Whoever that question was, I don't know. But usually async.io works on a single-threaded architecture. So it's different. Showing the true parallelism is like, also it requires a lot of boilerplate code. So using Celery, you can just, it's very easy to separate tasks. And you don't have to write a lot of code and a lot of stuff. But usually with async.io, it's a single-threaded approach. This is a true parallelism. OK, we are not using concurrency. We are using true parallelism. We are showing true parallelism with this approach. There's like concurrency and parallelism is very confusing. I've been working around with them for 6-7 months. Still confuses me a bit. But yeah, this is, you can use, like I showed concurrency, like there were different CLI commands, right? So we can optimize things accordingly. But async.io follows a single-threaded approach. So it's different. It's a little different.
Thank you. And is pre-fork model the default one?
Huh?
The pre-fork model.
Yeah, what?
Of the pre-fork
Yes,
pool is the default one in
yeah,
Celery?
Yeah, by default, pre-fork. So it will spawn all the virtual cores you have on your system. That's pre-fork.
And I think you already answered this during your presentation about Celery Beat. Yes, it's for scheduled jobs.
Yeah.
That's the scheduler.
You can schedule also. You can use it as a cron job. Like there's a thing called cron tab inside this Celery package. So you can schedule this like also like every 10 minutes or every 24 hours. You can do that also.
And can you elaborate more on the difference between RabbitMQ Redis and Celery?
I mean, like here, they are basically using it as a broker. So it's just managing a small queue. So all the tasks, like for all the functions are coming, they're just being funneled inside a FIFO order. So that's the like that's the only use of, and you also don't need to set up a lot of things. You just, if you're using Docker, you just spin up a Redis or a RabbitMQ container, just add that URL inside your config. I can show you that right now. Yeah, so you don't even need to you don't need to do anything. You just need to paste these links and configs of the whole container, and it will work. You don't need to configure anything else. Just need to specify like your time, because there's a time thing, scheduling. So you need it's specific or Indian Standard Time. You need to specify that. So there's config for everything. Yes.
And in a multi-server environment where I have one Django app for each server, what should I need to do with Celery Beat? Do I need one per server or just one shared?
No, no. So I mean, if you are, it requires, so for Celery Beat, for the scheduler, there was a different server. For workers, it's a different server. But when you use Compose, something like that, you can just add it like at one place. You don't need to start every time. Just add a Compose. That's easy to go with. I do that, but I'm using this local setup just to show you guys like how things are working differently and how I can play around with CLI commands.
And have you ever have an experience in running in Kubernetes?
No, I've never run it with Kubernetes, but I would most likely love to. Yeah.
And why do you prefer Redis over RabbitMQ?
What?
Why do you prefer Redis over RabbitMQ as a broker?
I like the red color, but yeah, just kidding. I mean, whatever you can. When I was beginning, I just got to know about Redis. I've never researched. I think RabbitMQ is a dedicated broker, message broker, but Redis itself used for caching a lot of other stuff. I mean, it depends. I don't think. I just used Redis because I thought it would be fast. That's it, and I like the red color.
Okay, thank you very much.
Thank you so much.
You can talk to him later.
Thank you so much.
Of course, you can talk to the speakers after the session for more questions, but we have a strict timeline. Okay. Now, Noam Katan, who's the developer at Ariga, is going to talk about Alembic and Django migrations. A big round of applause.
Thank you. Okay, so hi everyone. I'll just say that this is the first time I ever talk in a conference, so super excited, and I hope you enjoy. Thank you. Yeah, so the name of this talk is Beyond Alembic and Django Migrations. My name is Noam, as Jacob said. I'm working as a software engineer at a company called Ariga. I like hiking, so I found this picture of me just last year walking into Italy. So here I am again. A bit about what we do at Ariga. So part of what our team does is to maintain 2 fairly large open source projects. So this is a lot of fun and a big pleasure. The first one is called Ent. So Ent is an entity framework for the Go programming language, so an ORM for Go. It was started by the founder of Ariga, Ariel, when he was working at Facebook. And it was then open sourced, and now it is part of the Linux Foundation. So the second project is called Atlas. Atlas is a tool that lets you manage your database schema as code. So it's a schema migration tool, and it's based on modern DevOps principles. Okay. So today's talk is about ORMs. If your app reads or writes from a database, then you might use one. ORMs, object relation mappers. This is the layer, this is the component of your software, of your application that maps between your Python classes and your database schemas, and your database specifically queries and statements. So its goal is to provide an abstraction for your database to let you interact with it in your Python code. And while there's a lot of stuff to discuss about regarding ORM, there's a lot of interesting discussions like how they work or whether you should use them in your application or not. Instead, I want to zoom in today into a much more specific topic in the world of ORMs, and that is the subject of schema migration tools. Sometimes they're also called schema management tools, specifically the ones that ship with the popular Python frameworks. So, just as a short recap, what we're talking about. So, what are these data migration tools, schema migration tools, sorry, and what are they used for? Basically, as my application evolves, my data model changes, then my database schema would have to follow along. Which means that if, for example, I have this user model in my Django application, and I want to add the birthday attribute to it, so I want to start tracking the birthdays of my users, before I ever execute or before I ever deploy this code into production, I would first have to somehow execute this command on the database, because otherwise the code will run and it will start issuing queries, trying to read or maybe write from this column, and the database won't know what we're talking about. So let's see how it looks like on a framework, the SQL Alchemy framework. So we have our models defined as Python classes. So here we have a class called user and a class called match. We're tracking the results of a game of some kind. And we also have the migration directory, which includes the instructions and the scripts for the database to upgrade it and to create tables and columns as we desire. Now, let's try to edit the schema. So we will add, look, no hands. We will add the points attributes to the match model. And we'll see the change. So we're adding points. We want to start tracking the score of each game. Changes look okay. We're going to keep it. And now Copilot is telling us that we have to run this Alembic command. Basically what it does, it compares the state of our migration directory with the state of the schema and the code. And it produces a new generated migration for us. So lo and behold, we can now execute it and upgrade the database to match our schema. So everything until now is great. Overall, we can say it's a pretty great developer experience. Not only because Copilot is writing the code for me, but also because the Python community in general have really great frameworks, Django and SQL Alchemy. Each comes with its own abilities and its own schema management tool. And I don't need to understand how to define the models on my database. I don't need to know, I'm not a database expert, I don't need to plan the changes. I just need to state in Python code the way I want the schema to look like. And the tool that I'm using is doing all of the work. including generating the plan for updating the migration to the database to the next version. And this is overall a pretty great experience, like I said, and I think that if everything is great, maybe we can just stop now and we can go early. So what do you think? Okay, so of course I'm kidding. And what I really want to talk with you about today is the question of when you should, as a developer, consider an alternative. What are the scenarios in which you may want to be looking for a general purpose migration tool and eject from the default one provided by your framework? To explain this, I want to introduce a concept that in Ariga we often call the hidden bias of ORM native migration tools. And there are 2 points to that. So first of all, we are stepping into the shoes of an ORM maintainer for a minute. And I'll say that in order to provide a minimally useful product, I want my ORM to be useful, I have to ship it with some kind of schema management solution, right? If I'm only giving my users a way to interact with database schemas, but not a way to create and manage them on the database, then my ORM is basically useless. Ariel, like I said, who is the founder of Ariga, and he created the Ant ORM for Go, so he puts it really well. So what he says is that as an ORM maintainer, I see schema management as a necessary evil. I want to spend my time on the runtime API and performance optimization and not generating alter table statements. So what it means basically is that as an ORM maintainer, I want to focus on the differentiating factors of my ORM, making it better. I want my users to like my ORM. I'm going to focus on the factors that most people care about, which is the runtime API. I want to make a good developer experience in the runtime library. And I want to make my ORM fast. I want to make sure that it produces efficient queries. So thinking about the developer experience and the performance of the schema management solution is always going to be a secondary effort to me. It's always going to be lower on my priorities. And the second point is that, as we said, ORMs are supposed to be abstractions. The code that you run, that you write in them, is always supposed to run exactly the same, whether you're using SQLite or Postgres. And these are completely different databases. The way I'm going to achieve that is by only focusing on the lowest common denominator. I'm only going to provide you with the basic functionalities that any database supports. And if I don't do it, then my code won't be portable, and most ORM maintainers, they care about it. They want their ORM to be the ORM for a specific programming language. They're not going to break that abstraction. So what it means for us is that as developers, when we use an ORM, we are only getting the tip of the iceberg of what we could actually get from our database. Typically, we have tables and foreign keys and some basic indexes. But what we are not usually getting in most of the ORMs is stuff like functions and store procedures and triggers and views, etc. The list goes on. And a quick side note on that is that I know some people may be hearing me and they want to say, well, that's fine, right? Because I know about good architecture. I know that the database should be replaceable. It should be negligible. I don't want to couple the logic of my application with an external system. I want to use the repository pattern, so that's fine by me. But I can tell you, as someone who has been around as part of my job at Ariga, I'm talking to many development teams and many platform teams. I can tell you that a lot of teams really still do want to use all of these features, actually for good reasons. These pieces of software called databases, they are excellent in handling data efficiently. Some of them have been around for many decades. So there are plenty good reasons to use them. And just to name a few, we don't have time to go over the full course, but I can use, for example, functions and store procedures if I want to offload some of the heavy computation in my application to the database itself, where the data lives. I don't need to query the data, and then I can save some back and forth, serializing, deserializing the data back and forth from my backend and my database. I can use triggers, right? If I want to have some custom consistency rules of my schema, for example, I can express them in the form of code that will run every time the data is modified. And I get a guarantee from the database that it will stay consistent. So every trigger runs in the scope of one transaction, and I avoid any rest conditions if I do the validations in the application itself. Okay, I can use views, classic example. If I have, for example, a table that contains some sensitive information, I can use a view to I can use a view that only contains the non-sensitive parts, and then I can use the access control mechanisms of the database in order to make sure that only privileged users can get the table itself. In the same way, I can use materialized views. If I have some heavy queries, I don't want to compute them on the fly, I want to do it offline. And by doing it on the database itself, again, I can save some back and forth between the database and the backend. Extensions, if you are doing any kind of AI in 2025 and you're using Postgres, then you know about pgvector, also Postgres for handling geographical information, etc. And indexes. Okay, so as my application grows, my tables are becoming larger. And I may notice at some point that some of the queries are getting slow. And that is because they are not efficient enough. So one way to fix it is to improve the queries. Sometimes I can do it, but putting the right index can maybe greatly optimize my queries, the performance of my queries. Also, I've been in a talk before about partitions in Postgres, and someone asked, how do I use partitions in Django? So hope you'll get an answer soon, if you're here. Okay, what happened? Pause for a second. What happened if in our existing example from before, in our gaming application, we will try to add a materialized view, for example. Okay, so let's tell it, let's tell Copilot, please add a leaderboard materialized view, and we want to start tracking users, wins, and points. We want this leaderboard. It's a heavy query. We want to do it offline, and let's see what it says. So it's thinking, and it's telling us this. Okay, so basically, sorry. Okay. Never mind, basically what it told us is that the query, the materialized views are not supported in SQL Alchemy, so Alembic doesn't know about them. What it can do for us is to create a manual script, just basically the DDL definition. We can run it manually on the database to create the view, but we wouldn't, we can keep track of it for the future. Okay, so now we are responsible for we are manually responsible for managing the life cycle of this materialized view, all of its deployment. If it will change in the future, we don't get this magic that we saw before of automatically generated migrations for our view. So, if we want to use one of these advanced features, if we want to program on the database, if we want to still doing so while still keeping while still managing all of our schema with one tool that can do all of this magic of automatically generating migrations for us, then we need to be looking for a general purpose migration tool, one that doesn't have this bias that ORM natives tool does. And this is a good time to present Atlas. Atlas is the main project that we are working on Ariga. Its core engine and its providers are open source, and it is used by many great companies in production against real databases, and it's sometimes called the Terraform for database migrations. Now, I will show a quick demo, and sorry for doing it with AI, also all the demos with just talking to Copilot, but it's 2025 and I forgot how to code. So let's see. Same example as before, Atlas lets us manage our schema as Python code. Same classes, same SQL Alchemy models, and we also have the migration directory. This time it contains just SQL definition, just plain DDL for defining the models on the database. Now we can run the Atlas migrate diff command. What it will do, it will compare the migration directory for code, see if there are anything to update, and currently it says that they are synced. Okay. Let's now try to edit the schema. So let's try to add a new attribute to the match. Let's call it hello, I don't know. And we can run now the Atlas migrate diff command once again. What will happen this time is that Atlas will see the difference. It will pick up the change. It will compute a new migration for it and add it in our migration directory. So now we can deploy this new code to the database in production. Okay, so far so good. Now we want to see how we can maybe add a materialized view. Same as before, we're going to the chat and we're asking it to create a materialized view called leaderboard, and we want to track wins and points, and let's see what it does. Okay, so it's thinking and is looking at the configuration of the project. It's saying it's an Atlas project, and it sees that we are using a composite schema, which means that I can layer additional SQL definitions on top of my Python code. So that goes into this schema SQL file. So we will go there and update the code there, just adding the migration directory in the SQL file. And now, if we run the Atlas migrate diff command once again, then Atlas will combine the definitions from the plain SQL and from the ORM definition and produce one schema from it, and then it will derive a migration. So now we can apply it to the database. So we are happy. But we also want to make sure that the materialized view is working, right? So we will write a test. So let's go and generate a new test for the materialized view. And Atlas also comes with its own testing framework. So I can write simple test, as you will see in a minute. And basically just a simple test defined in a format called HCL. And just something really minimal, we're inserting some data into the view and querying it to see that we are getting what we expected. And we run in the test with Atlas schema test, and we see that it passes. Okay. Okay, so summarizing what we just saw. So using Atlas, you can still define your data model with Python code, same Python code as before. Atlas can load the existing definitions into the schema and manage them same as Alembic. Additionally, you can also layer extra SQL objects. You can utilize any database features that you want in SQL. And the diffing tool takes all of this into account and produces one schema. Plus, we also saw a demonstration of one of Atlas Pro features. There are many things and cool things to show and talk about, but there is a testing framework that can let you write tests, so you can make sure from now on that the schema is doing what it is supposed to do. Okay, this is all good so far, but as we know, in 2025, the job of a developer is not only writing code. Building application does not end with generating migrations. With the rise of modern CI/CD in the past decade or so, we know that the job of a developer has been extended to also thinking about how we deploy, how we deliver our app. So, just as a short recap, when I'm talking about CI, I mean everything that I can do to make sure that stuff doesn't break before I deploy it. So that may include maybe tests, or maybe my security team is requiring me to run some kind of security scanner on my code to make sure that it doesn't have any vulnerabilities. What about schema migrations? Okay. When I'm talking about CD, I mean that we want to make sure that we can deploy without human intervention whenever we want. Okay, so I don't want to connect to a server with SSH and upload files to deploy. I want my deployments to be automatic. I want them to be workflow based. I want to be able to control who deploys, etc. So there are a lot of modern tools for that. Now, migrations are a risky business, and you probably know it if you ever dealt with schema changes, schema migrations in production. There are a lot of things that can go wrong. There are a lot of ways where we can shoot ourselves in the foot. Just to name a few. We can have destructive changes. Okay, maybe my migration is dropping some tables or some column. If I do so, then the data inside of this table is now gone forever. I can undo the migration if I want to recreate the table from scratch, but without the data. Okay, I know that it maybe sound a bit trivial to talk about, but just last year, a company called Resend, they provide an email API. They had a major incident with downtime. And from the incident report that they published, we can see that this is exactly what happened to them. They had a migration, the migration dropped some tables, and the tables were crucial to the operation of the system. In their case, they had a backup, but still not a place you want to be in. I can have what we call data-dependent changes. So in the form, for example, of constraint violations. If I have a migration that adds a new constraint on the data, maybe it will pass on my local development database, because it doesn't have any data that violates the constraint, but in production it will fail. And what happens when a migration fails midways, depending on how things are set up, I may need some manual intervention to reverse things or to fix the issue, and again, not something that I want to find myself doing. I can have breaking changes, so obviously if I'm breaking the contract between the database and its clients, so for example, if I rename a column, then it may also break stuff unless I know what I'm doing. And yeah, table locks. So that topic is a bit more advanced. Basically, some schema changes in order to perform it, to fulfill them, the database will have to lock some resources. For example, a classic example for this, in MySQL, if I am editing an enum column, I want to add a new value to the enum. I'm not adding it in the correct place, and there's a subtle difference. Then MySQL may need to rewrite the entire table. If it's a large table, then this rewrite may take a lot of time. And during that time, there is an exclusive lock on the table. It's basically down. So what do we do about all of these risks? So Atlas was created with the understanding that not every developer is a database expert, but we still want to develop fast. We still want to have short iterations. So this is why we can use the Atlas migrate lint command. It's basically just a tool which is like a linter for migrations. I can run it on my migration directory, and it scans the migration and warns me about potential hazards. Here you can see that it's warning me about adding a unique index, which is a data-dependent change, and also having an operation that may require a lock from the database. So far so good. What would be even better is if we can run it also in CI. So this is why Atlas also comes with its own GitHub Actions, also integration with GitLab and Bitbucket and all of the major platforms. Basically just automatic code review on my migrations. Every time a new migration is created, it analyzes the migration and add comments. Here, for example, you can see that it's warning me about destructive changes. So if I want my PR to be approved, I need to either ignore it or handle it in some other way. So this is for CI. And now let's talk a bit about CD. So one of our observations is that regarding deployments, ORMs are not concerned with how you deploy. They don't have an opinion on how you get the database schema to match the code, how you deploy your migrations. Basically, if your team probably has any kind of deployment pipeline, you will have to figure out yourself how to insert this phase of deploying the database schema into your existing pipeline. If you're using Kubernetes, then you have to write the integration yourself. If you're using Atlas, then there are plenty of existing integrations. For example, you can use the Kubernetes operator of Atlas, so basically just making your database schema another resource in your cluster. If you are using Terraform, then you can make your schema just another part of your infrastructure. There's an Atlas provider for Terraform. Also, if you're deploying with GitHub Actions, there are actions for that. Also, once again, for GitLab, for Bitbucket, etc. Okay. Last point on when you should consider using Atlas instead of the default tool provided by your framework. So if you are in a team that writes a service that it's a polyglot, meaning you have multiple services and they are written in different languages, different frameworks, you have different database you want to deploy to, and you want to have one standard way to manage your database schemas, instead of using for each framework its own machinery, then Atlas, the same way we saw Atlas working with SQL Alchemy, we can also do the same thing. There are providers for all of the major ORMs in the popular languages. Okay, so wrapping up, we started by asking what are the scenarios in which you may consider using Atlas in your application. Then, first of all, maybe you shouldn't, because like we said, the Python community has really excellent frameworks with great toolings. If you're not looking for anything fancy, then that just might be enough for you. But if you want to use any of the advanced database features in your application to enhance your application, and you still want them to be these objects to be part of your schema that you manage with your tool, and also if you want to build a robust CI/CD pipeline, and you don't want to start reinventing the wheel and build in your own integrations. Also, if you are building a service that it's a polyglot, that includes maybe many languages and many different frameworks, you want one standard way to manage your schemas, then you might be, Atlas may be just a good fit for you. Okay, finished a bit early. Thank you for listening.
Thank you so much, Norm.
Thank you.
We have quite a few questions.
Oh, wow.
Okay. So how do you handle, you can handle migrations in a micro framework architecture where tables are actually shared between different microservices. There is something that Atlas can help in this scenario.
Yeah, so it was my last point, actually. The same way, you can actually define your schema the same. If you choose to define your schema in the form of one ORM that you're using, maybe the main application or the first application that was reading from this service, then you can do it with an ORM. But otherwise, there are a lot of different ways and data sources and forms to declare the state of your schema. So, yeah, you can use the same. You can maybe extend the schema with different sources, like we saw in the demo. Yeah.
And how do you handle large migrations that block table or have migrate data? Can Atlas help with this large database operations to mitigate the down?
Data migrations are not technically supported yet. It's on the roadmap. About large operations, for example, one example that we are facing at Ariga is we use a multi-tenant architecture, which means we have to redeploy the same migration directory once over and over to new databases. Which means that basically we add a lot of migrations, and the more the migration directory grows, then the operation is becoming slower and slower and slower because there are a lot of statements to execute. So one cool feature that we use from Atlas is a checkpoint. You can create a checkpoint migration. It just squashes all of the changes that you had so far, and then it runs much faster.
Thank you. And there are quite a few questions about the future support for NoSQL databases to help migrating the document schema.
For NoSQL databases?
Sorry?
For NoSQL databases?
NoSQL databases.
Okay, so I can tell you that we're currently working on some new drivers. I'm inviting you also to join the community on Discord, and we are getting requests, and we are basically just responding to what we see that most of the users want. Currently, there isn't any planning to support a NoSQL database, but if there will be demand for it, then...
Yeah, there was another question, exactly how to help expand the supported database, and you just answered that.
Okay.
And, sorry. Do you plan to, or do you already support migration merging like Django does, like consolidating multiple migrations in a single one to, I don't know, when you're creating new databases based on the existing one, instead of having a lot of different migrations, just consolidating in a single large migration?
If I understand the question, this is basically the composite schema that I demonstrated. Mm-hmm. You can actually define, we saw it in the demo. You can basically define a composite schema. I hope I understand the question correctly. But basically, you can define just a list of sources for Atlas to get the schema definitions from, and it will just manage them as one schema.
Okay. And if you need further clarification, you can talk to him later.
I'll stick around. Also, by the way, I have some swag. If that's appealing to anyone, then...
And how the testing of the migrations works? I mean...
Testing?
Yeah, the testing.
Yeah. Okay, so I also demonstrated it, but basically there's a nice format. You can define your tests in an HCL format, and you can put all your tests in one directory. And basically, you run the Atlas schema test or Atlas migrate test. Okay, there's a subtle difference depending on your needs. But basically, these tests are a really nice structure. You do a setup. Okay, so for example, you can insert data into your database, and then Atlas make sure to apply it. For example, the latest version to the database you are testing on. And then the setup runs, and then there are assertions, and at the end, Atlas does a teardown, so just cleaning the database up. So, yeah.
And does Atlas detect possible risks, when migrating between different databases, like migrating from MySQL to Postgres? Does Atlas support this?
No, so it's a schema. No, it's a schema migration tool, meaning it's there to migrate your database from one version to the next. data migrations and the transfer between databases, it's not in the scope.
Okay. And there are talks about Django ORM and migrating primary keys. And
I'm sorry, again?
Django ORM and migrating primary keys, I mean, probably the change between int and big int or something like this, I suppose.
So what's the question?
And how Atlas supports such large changes?
Large changes on the
Huge
Django?
Changes, I mean, probably in terms of long-term, long-lasting changes. Let me know if you write the question, and let me know if I have not explained it correctly, and you can explain yourself.
Actually, I think I understand the question. I don't have a response on the top of my mind, so maybe.
But feel free to
maybe you can
catch Norm later. Thank you so much. Lunch break is starting any minute, and session will.
Thank you.
Session will resume at 2:40 p.m.
Domande, tu preferisci farle alla fine o durante? Fine. Okay, questions are postponed to the end. So I think we can start. Actually, it's a pleasure to introduce Pietro. Pietro is a great person, great programmer, also friend of mine. So
that's why he's biased.
Yes, exactly. I'm a little bit biased. He's a data scientist and also organizer of Python Milano and PyData Milano. Yes, I'm so happy to have him here. So now Pietro is going to start and introduce us to NIM for Pythonistas.
Yeah.
What do you mean? Isn't you are in the NIM community, right?
No.
You're not Python. Okay. Right. So you're doing time series. No. Okay. No time series. So you're doing I don't know. Streamlit.
No.
Functional programming. Oh, okay. Domain-driven data science. Right. You do too many things. Okay.
Hi. So I want to talk about why I think that I have to turn it on.
Il pulsantino sopra.
This one?
Yes.
Okay. Yeah. Hi. I want to talk about why I think that the role of domain expertise in data science is important, and possibly convince you that it's worth investing more effort in learning about your domain. Slides are on GitHub. In the first part, I will argue about why domain is important and introduce the topic. Then I will share a quick intro about the domain I know best, which is logistics and supply chain. Finally, I will go over a number of somehow disconnected stories and ideas on how to make your data science practice more domain-driven. I will also share how a particular technical topic, like forecasting, can be shaped by the domain, and it's different for a particular domain. So we already had an introduction by Alessandro, but I'm Pietro. These are my emojis. And yeah, I have a math background, and a piece of trivia I cannot resist sharing is the fact that here in Bologna, more than a century ago, my great-grandmother graduated in mathematics. So, special place. I've worked almost 9 years in a company that sells a supply chain and logistics software, so that's where my background comes from the logistics part, and I know that part about planning very well, but and I'm also part of the community, Python and PyData, and in the last year I've been working in Agile Lab, and I will maybe say something more later. But let's go and introduce the main subject, which is the domain. So when I started in data science, which was a while ago, it was not at all evident what a data scientist does. Maybe it still is not, but something that helped us understand what to do was this so-called data science Venn diagram. I don't know if the young people in the room still see it, but it was a fixture back then. And this tells you that in order to be a good data scientist, you need to have a math, stats background, you have to have or develop skills in writing code, and then you put some domain knowledge sprinkled on top, and then you're a good data scientist. So you go and you start finding a lot of content about the math part. You study it, you learn it about all the algorithms. Then you learn all the cool frameworks and libraries about code. And then you look for the domain and say, okay, but what it is the content about domain? How do I learn it? And my impression, at least, is that there is where we have less content, both in quantity and quality. And this is one of the motivation for this talk, to share what I know about the domain that I learned, in order also to inspire you to share about your domain, because I want to learn about other domains. One of the reasons why I think it's important the domain is because I think it's crucial for the success of a data science project. As technical people with technical background, we tend to think that the success is based on the technology, on the quality of the data that we have, on the quality and the accuracy of the model that we produced, and maybe also on the smooth and the implementation. If we have this in place, we have a successful project. When you grow a little bit more, you learn that things are not like that. There is another side of the story in which you have to convince the stakeholders, which are business people, they're not technical people, that the thing that you have built is valuable. And once you have convinced them, this will be used, and you will have reached the holy grail of data scientists, have something in production. Which is not so easy as it sounds. And one of the theses of the talk is that the domain helps you a little bit on the technology side, but also helps you a lot on the business side in order to communicate with stakeholders and prove and focus on what is valuable, and so reach the holy grail. The name domain-driven data science is inspired by a couple of things, something that is called domain-driven design in software engineering, not much to do with data science, but it's a practice in which developers started to understand, hey, maybe if we write the software and we know what we are writing about, not just know about the code, we write better software. And this has started a big industry in this topic, in which developers try to have a common language with business people. And this, in turn, has inspired, applied to data engineering and data governance, something called data mesh, which is really started as domain-driven design applied to data governance. There is, I think, in general in the data world, a trend about trying to apply best practice from software to data, and this is one of these trends. And as a company, it's something that we have built a part of our reputation also in being expert in this kind of things, and we have released in the last year a short 1-hour free course on the topic if you're interested about it. But these are off-site. So let's go, and in the main part in which I share you what I know about the domain of logistics and supply chain, which is, I think it's an interesting, old, and not so well-known domain, maybe, for some of you. Maybe some of you know it better than I. So let's start with logistics. Logistics is one of the oldest domain because the classic quotes you find in handbooks are about moving goods for war, for example. These are classic quotes. And it's defined as the process of managing the things, materials stuff, goods that you buy, you move, and you distribute in order for customer to buy. And in order to decide how much to buy, when to move it, where to move it, how much to move it, and where, you need to match this with the information flow that comes from the market. And two of the main things that a logistic network deals about are storage. You have to put the goods somewhere, usually some kind of variation of warehouses, but it could be also the final point of sales. And you need to transport with containers, with ships, with trains, with people walking, or something like that. And traditionally, also in the past, if you think about data science or AI applied to this domain, you might think about, okay, let's automate this kind of things. For example, you can thinking about automating warehouses. This is something that is, I mean, it's part of the things that are done. But I think that there is a big part of the data science part that is interesting, that is not related to this. Also because this kind of automation is something that requires big investments and tends to have time to take a return on investment. Instead, there is a part of the supply chain area that is mostly dealing with this information flow and using it effectively. And in order to motivate that part, I want to introduce some of the elements about modern supply chain. And supply chain is a term that was invented by a consulting company, Booz Allen Hamilton, in the 70s in order to sell this kind of stuff. And the thing is that in the last 40, 50 years, companies have become more interconnected. You have in a more extended network of suppliers. The market changes because the market are more demand-driven in the sense that in the past you used to buy what you find in a supermarket. Now you go and look for that. And you're also used to an increased customer experience. So customers have more demands. And companies in supply chain have found out that with best practices, they can compete and increase both on having an efficient operation, so reducing the cost of the operation, the cost that it takes to move things around, to hold it, to hold capital in stock or something like that, but also in service. Service is the other part of the equation in supply chain. So the fact that when somebody asks you, do you have this, I want to buy it, you say, yes, I have it, okay? And you have it prepared, and you need to prepare beforehand. In this context, supply chain are frequently disrupted by, I don't know, a container that gets stuck in a channel or volatility with respect to border events. So it has become more complex to manage this information part. And this is where planning comes in. So in the previous company, we made a tool for planners that worked only on the intelligence part. It didn't touch anything, I don't know, inside your warehouse or inside your containers, but it was just moving stuff about data. So that's why it's good for data scientists. And planning in the content, planning means to understand what's going to happen and prepare for it. But in the context of supply chain, you can divide it in 3 parts. So there is one part that is about the demand. You need to understand the historical demand of your customer, and you need to be able to forecast it. And the forecast needs to be probabilistic for a reason that will be clear later. And this is where the part of forecasting that I will deal with later comes from, the need for good forecasting capabilities. You need to forecast it because you will have a stock that evolves, and then at some point you will decide to make orders, and your stock will go up. You don't want to. You don't have an infinite warehouse, so you have to order little by little, time by time, and the stock will go up and down. And the important things tying these 2 parts together, demand and stock, is service. As a business, you decide for different categories of product which kind of service you target. On this part of the service, I don't know, spare parts for luxury cars, I want to have a very high services because these are pricey customers that want to have. They want to order it, they spend a lot for a car. When they need a spare part, they want it right away. And a service in this context means the percentage of my orders that I'm able to satisfy, as a simple definition. And the more you want to be able to satisfy, the more stock you will need to keep because of the fact that there is uncertainty. So the main technical thing which makes hard the whole process is one of the 2 things that I will talk about is uncertainty. And there are 2 things which are uncertain, both the demand of the customer, it's not stable in time, but also the supply. And this allows me to introduce a couple of concepts which are central to this and explain you why forecast is probabilistic, which is something I anticipated. So if we go back to that diagram in which you had stock at a certain moment of time, there is demand that decreases my stock, and at a certain point I decide to place an order. The moment I decide to place an order, the order does not magically arrive, because here we are talking about physical goods. It's not ordering software or something like that. So the goods takes time to be shipped, to be produced, or something like that. And the time between the moment you place an order and the moment the order arrives is called the lead time. And this is something that already in itself is probabilistic. One of the reasons why supply is uncertain. Usually it arrives in a week, but this time it arrived in 2 weeks. And you need to model that probabilistic. So the fact that there is a lead time, that is probabilistic, and also during this lead time, maybe you thought the demand was going slowly, but it went much faster, your stock can evolve to the moment in which it reaches the 0 level and you have a stock out and you cannot satisfy the orders and the customers are not happy about it. So in order to deal with this variability, in this domain, there is one of the pieces of stock that, conceptual pieces of stock that you deal about is so-called safety stock, which is extra stock to mitigate the risk of stockouts. And this is directly proportional to the forecast variability, so the distribution part of your forecast. And that's why, in this context, you need a forecast that is probabilistic. So this is the fastest and the simplest I could do about explaining some of the concepts to motivate why we do some kind of forecasting technologies. Something that I want to mention, but I will not talk about, which is the second big area which makes supply chain planning complex, is the existence of constraints which exist in life. You have capacity constraints, you cannot produce so many, you cannot order so many, you have capacity in terms of storage or time. There are integral constraints. You order stuff in multiples. You have minimum quantities. And then there are, in general, other types of constraints, feasibility constraints like schedule, opening hours. And this is a big part of the complexity of this process. And for this, the type of technique is operational research. I would say that the main techniques in this context are forecasting and operational research. I will not talk about operational research. Instead, I will talk a little bit about forecasting in the concept of supply chain. So, in this context, the first thing that you need to do, so forecasting, it is about time series. So in a sense, I was speaking a little bit about time series. And the first thing that you need to do is to model, decide how many time series you need to forecast. And if there is a structure around the time series. And usually you need to take into account and decide how to model 3 dimensions. The product dimension, usually for a supply chain, you need to be able to forecast at the lowest level of aggregation, the SKU, the stock keeping unit, because this is what you need to decide to move around. But SKUs maybe have a very high noise, and SKUs come in family, brands, division. There is a product hierarchy on top of that you can take advantage of, the different level of the hierarchies, because they have business meaning. On the other side, the same kind of products, you will ship them to different regions. And air conditioner will be shipped with different demand pattern in the northern hemisphere or the southern hemisphere. So you need to take into account these 2 different dimensions. And the market is something that for sure you will need to take into account the fact that you will need to forecast the demand coming out of a single warehouse. But maybe the same warehouse serves multiple regions, different customers through different channels, from the e-commerce channel, from the retail channel, from a partner's channel, and maybe it makes sense to separate the demand according to this dimension, because you get a better signal. And finally, you need to decide what kind of minimal unit of time. You need a daily forecast, a weekly forecast, a monthly forecast. For stuff like spare parts that move slowly, monthly forecast is the way to go. You don't want to go weekly. And in order to go daily, you need to have a business case that supports you, because if your lead time are monthly lead times, you don't need a daily detail of forecast. Because by the moment you change the forecast daily, it does not have any impact on the lead time. And so just to have an idea in terms of numbers, if depending on an industry, a company can have from dozens of products to millions of different products. If you go into electronics, e-commerce, you have a number of them. Markets can be a few or 1,000, depending on how you model them. And the time, depending on the unit, you can have, I don't know, the 12 months times the number of years, or the 52 weeks, or the 300 days. So basically, the data set size is not very big. Just to give you also an idea, is tens of thousands, tens of billion range, this is the kind of thing that we deal with. So now you have model, you have your time series, you need to understand the algorithms you want to do. And something that I like to start with are the most basic model, and something that is used in supply chain in time series forecasting and is not so well known because I don't know the classical ones are more well known are RIMA models, is a model which is called exponential smoothing, which is very simple and very stable, in which you update the average of your estimate with the latest value and the weight alpha that can be something from 0 to 1. And starting from this very simple model, you construct a more complex model, adding the things that you model with exponential smoothing. If you model with exponential smoothing a trend and a seasonality, there's something that in the literature is called as hot winters. If you model for intermittent demand, the moment in which the demand is non-zero and the quantity when the demand is non-zero, you have something that is called Croston, and there is whole part of a hierarchy of models like that. And recently, of course, machine learning has had an impact on these statistical methods. And let's say that the category of methods that you use and that are used are machine learning methods. There are still enough data so that they call for something like GBM instead of XGBoost in some cases. Neural methods can be very specialized. I don't think they're at the moment so widespread. And recently we're starting seeing foundational models. But they may have, it's not something that is very widespread at the moment. You put in place your algorithms, you pick the one. As a data scientist, I try to have a very simple baseline and then take into account the complexity, and you need to start evaluate. So the metric you need to take into account, the classic root mean squared error is a classic metric. Something that I think is useful and is not so evident is the bias in terms at different level of the hierarchy, at global level, at different level of the hierarchy. And this is something that, for example, machine learning staff needs to have special care in order to have a good bias that takes into account the trends and everything, because you want to have, in general, a forecast that is unbiased, that you do not systematically order more than you should or less than you should do. And another one that you can use, let's say that these are the basic three, are the mean absolute error that is more resistant to outlier. If you had demand with peaks, maybe this might be more interesting. Something that is very well used in the industry is called MAPE, which is a very bad one because it's biased, and there are articles, and I link one, telling you exactly why this is not a good measure. And I think one of the things that is interesting is that evaluation then can be very custom and very complex. And something I want to mention is something that happened now a few years ago that is called the M5 competition. Is part of a series of competition on forecasting, but that specific occurrence was on data for supply chain, data from Walmart, from a retailer. And I think that has been a bit of a milestone in this domain because it was an open competition with open rules, a complex way of evaluating with aggregating a weighted root mean square scaled error, because the root mean squared error is not easy to use it when you have to aggregate time series of different dimensions, when you have to compare something that orders very little and something that orders a lot. And so that's another thing that you want to go deeper, is something that is a very interesting read in this subject. Finally, in order to give you another ideas of the things that you can do with data scientists in the forecasting context in supply chain, something that was actually my work in my past company, was to work on engines that dealt with specific effects. So one effect that you have, which is very important, are seasonality, sun creams, ice creams, air conditioners, but also tires are ordered differently in different times and different markets. And this is something that you need to take into account of. And maybe the signal that you have at the lower level is not easy, so you need to aggregate, and maybe you're using some clustering techniques and some aggregation in order to do that. Another classical thing, some industry rely a lot on promotions. Yogurt producers can sell up to 30–40% of yogurts in specific period only on promotion. And when you have a signal that goes like this and then bumps, and like that, it's not easy to make a forecast. And so you need to separate this discrete event and model the uplift separately. And another kind of problem that happens in other industry, like fashion industry, in which you have like shoes or glasses, in which you launch a lot of models every year, is the problem of initialization. Because the classical problems of forecasting is when you have a history long enough. But when you have no history, you have to provide an initialization based maybe on the fact that usually product in this category and this market start at this level. And so that's, for example, one of the classical applications in which you might want to be tempted to use machine learning in a classical way as a regression model. I did a presentation of forecasting. I think one of the set of libraries that did a great work in making the Python ecosystem very strong on time series forecasting is Nixla. I did it back then, and I redid it, updated recently, and actually something that I could have added is that one of the most important textbooks in time series forecasting, Hindman, which was R-based, last month got its first Python edition done in collaboration with Nixla people. So that's a new reference that for Python people in the last 5 years, we've gotten a very big boost in terms of what we can use. But that's not the topic of today, the code and the math part. There's always the temptation to go and nerd out about that kind of stuff. The topic of today is domain. So the last part is sharing stories and ideas on how to make your data science practice more data-driven. The first one is the story when I was building one of these product to initialize a forecast, so to forecast a new product, the sales of new products. And we built this model, and we set up the metrics. There is a baseline starting from a process that is done asking around people through Excel that are shared and takes about a month. Instead, we build something in which you press a button, and you have a number that is provably better than the number that is shared. But the problem is that the user don't want to use it. And this is difficult, and for example, one way that we try to go about is to add in, because there was no trust in the model. They see this as a black box, and they say, oh, I don't understand the process. So one way we went about trying to say, okay, I add sharp values, I explain you how this forecast is produced. Does this help? And for me, my lesson learned is not so much. Maybe another direction could be build a forecasting process that is more structured about how they go about the domain. That maybe has some interest into about, because usually they go in a top-down in which there are regional managers that produce forecasts because they know their market and then break it down. And so and you can take better into account trends and everything. So maybe you have to rethink your modeling approach because of the domain. It's not just about the metrics and the evaluation. So this is at the end of the process in which you have built something and you wanted to use it. But at the beginning, you're looking at data. And so on a more smaller case, one of the other things in which I think it's important to think about the domain when you deal with data is when you are starting to exploring the data and looking at the data that you have. And this is a story when I was exploring warehouse data. So stuff that comes in and comes out of the warehouse. And you have order data. And then I look at the data and I say, okay, there are a lot more rows for outbound orders than inbound orders. But I kind of think that in a warehouse, the amount of stuff that goes in and goes out is the same. So why is this happening? This is happening because, well, in warehouse, stuff comes in into pallet like this. In boxes, you have a supplier that gives you a pallet of the same stuff. But usually, warehouse distribute to point of sales, in which stuff goes out like this, in which your order is not one line of the same stuff, but it is 100 lines of different stuff. And so that's why you have this complexity between the stuff that comes in and the stuff that comes out, which also explain why the picking operation in warehouses is the most costly one, because you have to have people or some kind of process or technology that sorts out the stuff that you need to distribute. And maybe sometimes there is missing data in your order. And when there is missing data, I think you very often need to think about the domain. I mean, it could be a vacation, but it could also be that the Wi-Fi went down at the warehouse and there is no data for the day. And you need to take into account that, and you need to know that. And the other thing that where I think a domain makes an impact is considering one of my favorite rules of machine learning that is also sanctioned by a set of Google guidelines, which is the first rule of machine learning should be to start without machine learning. For various reasons, because machine learning introduces complexity. So if you have a simple heuristics that solves the problem, you should use that one. And you should always start with something simple and evaluate against your more complex model in order to let's say, communicate the value of this added complexity. So you need to evaluate, and then it's better to have in that than a machine learning model which handles the complexity itself than a set of complex heuristics and set of rules to maintain. This is something that the industry has shown. And I think that the domain helps usually in picking simple heuristics that are good. And maybe that simple heuristics also are what you will use in a perimeter that is outside of what you can predict with machine learning. And so they also do some part of the work. So how do you know about the domain? So I think one of the important things that as data scientists we need to be able to learn how to do is to talk to experts. People who are not technical and who know their domain, and you need to establish a language and you need to be able to learn with them. And so something which is important is also to practice the interview. You usually have some kind of stakeholders that you need to be in the interview, and you need to be able to understand what they're saying and where there are opportunities to show value and risks that they do not care because they think that what you do is magic, while instead there is nothing magic, we do not extrapolate, and the data quality is always important. So you need to be able to communicate with them. Something that I think is very useful when interfacing with experts is to provide some kind of interface. So another talk that I did was a talk of Streamlit that I've used a lot because it's a very practical tool to talk with experts because they also find a nice UI. So I think that some kind of interactive tool that shows the data you're dealing with is important to talk to experts and have them connect with the data, which usually have trouble doing that. Another thing that you can do with the domain, so we know that documenting code is good, but maybe we should start documenting the domain, or at least a little bit of the domain. Something I started to do in my projects is add very few lines in the README, which I called the business, domain, and data essentials. It could be very, very few lines, but it helps you anchor your problem to the business value, to the specificity of the domains, and to what you actually have that should provide value, which is the data. So you might have a specific project which tries to improve a process by reducing cost. And in that domain, or reducing cost can be in improving a specific process, and there is a common way that is used to improve that specific process, and you should track it down because this is something that people know, and you need to be able to improve on that. But you also have to keep into account the data that needs to come from a system, and you need to know a little bit of the specificity of the system. Warehouse management systems that have their own life cycles, how many years of data, what happened during that data. Usually, they start to implement process, and you have good data from some moment on. Okay. Another thing is that you might want to learn about the domain. And there are a number of ways to do that. There is no shortage of influencers nowadays, and I think they are a useful thing. Sometimes they are incentivized to talk about a lot of stuff and complexify stuff. But when I start working on the project, I try to find these influencers nowadays on LinkedIn or in other places and try to read, because these are people specialized in the domain. And this Nicolas Van de Putte is one of the people that is doing a lot of work in the forecasting and optimization domain that I cited a couple of times. You should rely on experts, and not only the experts you find in the project. Something that I discovered is that, well, in YouTube you find really everything, and I don't think we realize how much there is, but now that we see this LLM and AI that creates magic stuff, it's because stuff is there in YouTube, in corners that you don't know of. And I was working for the first time on warehouse stuff, and I found these two guys, warehouse experts, very basic, no data, no nothing, that explain you all the basics of the process. And the next process, the project that I did on something that was network, I go and look on YouTube for simple people that explains you that. And when you go to a meeting for a customer or for your stakeholders, that you have watched a 5-minute YouTube video on that topic, you have a much better performance on the interview process and what you can extract in terms of information about the domain for the interview. Finally, if you are investing in a specific domain, you should also study books. And another thing, but this is just purely speculative, is something that sometimes you might want to get inspired by the domain. So one of the last projects I worked on was in this warehouse concept. There are these lean processes by the Japanese in which they try to put in a warehouse, they need to sort everything, straighten, make it shine, because when everything is clean, people work better. You have to standardize, and I don't know, this kind of methodology is something that for me, it reminds me a lot about a data pipeline. So I'm still tempted to write a 5S methodology for data cleaning or something like that. At some point, maybe I will do it or not. Okay. So, I hope I have convinced you that the domain is a worthy and relatively untapped opportunity for data scientists. Maybe you realize there is more complexity, more intentional things that you can do in these things. It's not just something that, yeah, there are the domain experts, I lost them, but we can learn as data scientists. We don't have to become domain experts. We have to become data scientists expert in the domains. And hopefully some of you will be inspired to learn more and share, because I want to watch your talks about your preferred domains. So thank you for listening. And I work now in Agile Lab, which has a public handbook, which is a nice thing to learn about how a company works. And a couple of things that, if you want, you can ask me later, is about our self-management system, which is also an innovative way of managing your work and distributing authority and accountability. Or we have a number of other benefits, like a nomads program where we work from places like Canary Islands a couple of weeks. Thank you.
Thank you very much, Pietro. I have a question, which is, sometimes domains are great, and you dive in them a lot, and you can lose them in them, yourself in them. So how do you stop? How do you know that you know enough to solve your problem?
That's with everything. Also with the technical part, you can dive and can know how to stop. I think the important thing is to realize what's the goal of the thing that you are doing, and try to start from there. and try to do only what's necessary for the next step, trying to go...
So try to have an iterative...
I don't know, I try to make it simple, to clarify very simple the goal, and then try to understand, okay, but these things in which I want to nerd out, is it really necessary or not? And the other thing I try to do is I pack it as a nice to have, and I say, okay, these are the important stuff that I need to do first.
Okay.
And if I've done that, then I can do the nice to have. I never get to the nice to have.
Okay.
But I'm happy anyway, because the important stuff turned out to be more interesting enough.
Okay, thank you. Yes. There is another question from Francesco who said, I tried reading the blue book about the DDD, but it's so boring. I couldn't get past the first chapter. How can you help me?
There is another reference, which is an interesting one, which is Cosmic Python. There is a book that tells you about architecture patterns and domain-driven design done by two Pythonistas, not by Java people. That's why you find the domain-driven design book boring. So cosmicpython.com. The name of the book is different. They wanted to publish, it's an O'Reilly published book. They wanted to name the book Cosmic Python. And there is a reason for that. You find it on the website, but the editor didn't allow it, and so they registered the domain, of course, which is what you do. And the name of the book is something more enterprisey.
I don't have any more questions here on Slido. I don't know if there are any in the audience.
There is a coffee break.
There is a coffee break. Okay. Yeah, so if there are no other questions, last round of applause for Pietro.
Thank you.
Thank you very much.
Sono mesi,
solo fare un annuncio, dire. Excuse me. Can you please squeeze yourself, fill the empty spots, so if people new people are coming, they can sit easily without bothering the others. Thank you very much. So I do defragmentation for work. Do you defrag your file system often? I don't.
Di cui 2 erano laurea, anzi 3 erano laurea. Oh, quelli non li ho contate.
It's a pleasure to introduce Pietro Mascolo. Okay, Pietro is a data scientist and engineer, worked with machine learning applied to graphs. That is the subject of the topic. If you want to know more about him, you can go on his website, thecluelessdatascientist.com. Thank you, Pietro.
Thank you, Alessandro. Good afternoon, everybody. I'm very happy to be here in Bologna today and to see such a full room. Really warms my heart. I hope I'm not going to disappoint any of you.
Well, at least not most of you. Anyway, as Alessandro said, my name is Pietro Mascolo, and today I'm going to be talking about graph machine learning in general with a few examples. I do have a blog that Alessandro mentioned. I don't really update it very often, so don't be too disappointed if you visit it. Anyway, let's move on. You can find the slides and the code for this talk at that URL. It's just a GitHub repository. Today, I'm going to walk through a few things with you. I'm going to give you a very high-level introduction about myself and what I do. I'm going to talk a little bit about graphs in general, what they are, how can be used, and how they can be useful for machine learning. And then we'll talk a bit more about how we can use them specifically using Python, first with NetworkX, and then building more complex and sophisticated models using PyTorch geometric. And we walk through a real-world example-ish. I was hoping to work with a more concrete example, but I have to work on my laptop, which is old. So I did my best. A couple of words about me. My name is Pietro, as you've been repeated a few times already. I'm also using emoji as the previous Pietro to present myself and my history. I have quite a few countries in my flags. I was originally born in Brazil, but I grew up in Italy, actually just in Modena, 30 kilometers away from here. Now I'm based in Ireland, and I ended up marrying an Indian woman. I'm a husband to Pallavi, and I'm a father to Arav, who are the love of my life and the source of most of my gray hair. I have been working as a data scientist and an AI engineer for the last 15-ish years across many different domains and many different companies, mostly in Ireland, but I have a past here in Italy as that as well, which was very interesting. A lot of my former colleagues are actually here with us today at the conference, some of them in the room. I'm always happy to see them again. I am passionate about a lot of things, mostly technology related, but I also have lots of very expensive hobbies, which include photography, ham radio, hiking, and martial arts. And if you're looking to get in touch with me after this conference, you can probably find me on most social media with my handle at IZ4VV, which is incidentally my operator name as a ham radio operator. So what are graphs? I'm sure that some of you might have encountered them. Actually, how many of you have worked with graphs? Oh, great. More than zero. It's considerably more than zero. I'm very happy about that. So I'm going to skip over very quickly about the introduction. I don't want to leave it completely off because some people might not be as familiar as you. But graphs in a very high-level representation and description are essentially a way to describe relations between entities and a collection of entities. The relations are called edges or links, and the entities are called nodes. And these can be many things. We'll be mostly looking at homogeneous graphs in which you have nodes and entity and connections and edges that are of the same type, but you can also work with more complex heterogeneous graphs that have many different types of nodes and edges interacting with each other. And one thing that we need to understand is that graphs are everywhere. Even things that we don't think of as graph could be potentially represented as graph. And I have a couple of examples here. Actually, one of the very first problems that was solved using a graph is the famous problem of the 7 bridges of Königsberg, which was a riddle. We were talking about Euler, so we're going back a few centuries. And the enigma was essentially, is it possible to cross all the 7 bridges in the city of Königsberg without crossing the same path twice and crossing each bridge exactly once? And if you just look at the map, you might end up working many possibilities. But if you simplify the map and just look at the graph, it's fairly easy to say that the answer is no. And that's why we use graph. They're a simplification of reality. Some examples include social networks. It's probably the most illustrious example that we can think of, where people are nodes and all the friendships and connections are represented by the edges. Or we can go to more complex graphs, for example, fraud detection rings, or e-commerce, where you have multiple types of nodes and edges interacting, where you can have, for example, nodes that represent customers and edges that represent orders or that represent complaints, or and other nodes that could represent, for example, suppliers or other entities. And lately, there's also a lot of use of graphs also in biology for protein analysis and protein discovery. But there are also plenty of other data structures that we don't usually think of as graphs, but could be represented as such. Like, for example, images. Like, if you really wanted to, you could think of an image as a graph where each pixel is a node, and each connection is each neighbor pixel to the one you're looking at. That's a possibility. Probably not the most efficient representation, but it works. Text could be looked as graphs, where you have a direct connection between each subsequent word. As I mentioned, proteins or molecular structures could be looked as graphs, and there's actually lots of work that we're not going to be touching upon too closely, but it's quite interesting in terms of protein discovery or, for example, predicting the toxicity of a compound. And then, of course, social networks and how people interact with each other. This is from a very typical toy data set, which is close to my heart because I've been practicing karate for coming on 30 years now, which represents how people interact with each other. And you can predict how communities form based on the interactions. OK, I think we can go away with the introduction, and we can start talking a bit more about how do we use graphs in machine learning, not just at a high level. So traditional machine learning generally struggles with some sort of relationship-heavy data. And it tends to ignore a lot of the features that we could use. Graphs are great because they allow us to understand not just the structure of the data, but also relationship among entities. They can help us working on problems like node classification or link prediction, for example. Is it possible that a connection will form between a potential client and one of our suppliers? Is it possible that a certain transaction is fraudulent or not? Or how likely is it? Or graph classification, like predicting the type of a molecule and so on and so forth. And in general, these are data representations that are very well suited to represent and analyze very complex relationships patterns. And there's plenty of different types of problems that you can solve, or at least analyze and work on using graphs. As I mentioned a couple here in node classification, is in determining whether a person is trying to commit fraud or not, or graph classification, for example, trying to understand what type of a molecule you're looking at just based on how the atoms are arranged. There are also plenty of regression problems where you're trying to understand the numerical value that's associated with a node or an edge or even a full graph, like, for example, a molecule's toxicity. And then there's all sorts of more complex problems that can start ranging all the way into Gen AI, into generating new graphs. But we're not going to go too deep in that. Graphs with NetworkX. So NetworkX is a library, Python, of course, this being a Python conference. And it's used to represent and analyze graphs. I'm not going to go too deep into this, but there's plenty of things you could do to analyze your graph just by using this library. For example, here, we're generating a very simple graph. We're adding a few nodes and with connections between them, in this case, just 4 people, and the way they interact with each other. And we can easily visualize the graph. Sometimes just the visualization actually helps a lot in understanding the patterns and the structure of the interactions. Or we can start analyzing a bit more in detail some properties of the graph. So what kind of nodes do we have? How many edges do we have? What is the degree of each node? Or which is the node that has the highest degree? And by degree, we mean the number of connections that the node has, either inbound, outbound, or total. We can also try to find what is the shortest connection between 2 nodes. This is especially useful in very complex graphs. And it's essentially what most of your GPS navigators would do, trying to find a route from place A to place B. How do we represent the graphs, though? That's a very big problem in machine learning, because what we usually do is use something like this. This is called an adjacency matrix. And what you're seeing here is the graph of interpersonal connections of the characters in the Othello by Shakespeare. And it's not obvious, but these 2 matrices represent the same exact graph. The problem here is that when you use this representation, the order of your nodes matters a lot. So as is this sort of representation like this doesn't really work for us, because we want something that is not affected by permutating the nodes. Like we want something that's as stable as possible for mathematical work, of course. So there are ways to obtain what we call a permutation invariant representation. And one of the simplest one is just by using what's called an adjacency matrix, which describes how each node is connected to every other node in the graph. And NetworkX and a lot of other network tools allow us to do exactly that. In this simple example here, we have an adjacency list, which represents each node. There's a row for each of the nodes in the graph. The first element in the list is the node itself, and the subsequent elements represent the connection that that node has with other nodes. It's the most concise way to represent a graph, which could become very big. Sometimes we're talking about millions or billions of nodes, so concisiveness is a good thing. And I didn't mention before, but each node and each edge could also have additional properties associated to them, and they usually do. And that's usually what allows us to make predictions or make inference about the type of graph and the type of network that we have in front of us. Okay, we just had a quick look at how to represent the graphs, but how do we use them in an actual problem? How do we use them in a mathematical sense and in a programmatic sense to solve problems? There are many simpler types of algorithm, but for today we're going to focus on what is called a graph neural network. A graph neural network is exactly what it sounds. So it's a neural network that instead of acting on tabular data or on sequences or on images, it acts on a graph. And the way such a graph learns is it learns a representation, an embedding for each of the nodes based on the node's attributes and its neighbor's attributes. And it generates an embedding that can be used for future inferences, or it could be used in a subsequent neural network or other model for predicting something or for classification or what have you. And we're going to focus specifically on just one type of architecture for graph neural networks, which is the graph convolutional network. If you're familiar with a regular conventional convolutional network, the way a graph convolutional network works is pretty similar. It's just that instead of looking at the neighboring pixels of a single pixel, you're looking at all the neighbors of a node with each convolution. That's a very simple analogy there. And the mechanism through which each node learns through its neighbors is called message passing, which is actually very similar to its convolutional analog. So the node gathers messages from its neighbors, so the value of the attributes and features of the neighbors, or the edges that connect them. These are aggregated together, and then through a small neural network, the node embedding is updated. I promise this is the only slide with maths. So the mechanism is probably very familiar to you if you have worked with neural networks. You have an aggregation of signals with a certain weight matrix that is learnable. And you have a nonlinearity, or sigma, which is usually ReLU, but could be any type of nonlinearity. Some work, some don't. And that's what you get at the next step. You compound these steps a few times, and you have a graph convolutional network. Very simple. Kind of. Convolutional networks for graphs are only one of many possible architectures. There are some that have a very similar analog in the conventional space, if the slide progresses. For example, we have graph attention networks, which, as you can imagine, introduce an attention type layer. It's not exactly the same thing, but it's very analogous to what you would see in a neural network with an attention layer. You have graph sage, which is actually a fairly interesting type of architecture, which introduces not just aggregation. It could also, in some cases, include an attention layer itself, but it can generalize to more advanced types of pooling and even using LSTM layers to learn over time from each neighbor of each node. And then you have also isomorphism networks, which are trying to learn the structure of the whole graph at different scales. using perceptrons, really. And they can be used to detect changes over time in a graph, which could be useful, for example, if you're running some sort of problems in the space of fraud detection, because like fraudsters tend to evolve in terms of their behavior. So in a nutshell, what GNNs do is they learn all embeddings. They have a mechanism called message passing, and that allows each node to learn from its neighbors over multiple paths. And they can be useful for all sorts of tasks. Let's have a look then at a very quick implementation. I try to keep it as simple as possible, and I also have a very short benchmark later on to show you how these networks compare with more regular techniques. I'll be using a library called PyTorch Geometric. Has anyone here ever used it? Ooh, three hands? Okay, 4 hands. Okay, not that many. So as you can imagine from the name, PyTorch Geometric is part of the PyTorch ecosystem. And in many ways, it's an extension over PyTorch, just including new architectures that can be used on graph. As you've probably seen with most other architecture, this also inherits from module. And we have a new type of layer in this case, and we actually have many types of layers, but we're going to use the GCNConv, which is a graph convolutional network layer, sorry, so this is a layer. And we're going to use 2 layers. One thing that you will see that tends to be quite different between conventional networks and graph networks is that graph networks tend to be quite shallow. And the main reason is because, well, you're essentially running a small neural network on each node of a graph. Imagine having 1 billion nodes. Each of those has a small neural network running on top of it. It gets inefficient really fast. Anyway, back to us. So it's a very conventional network in our case. We have 2 convolutional layers. We apply one, we add a nonlinearity, ReLU. We apply the second, and we have a softmax. Very simple, very conventional. Training, again, PyTorch makes things simple for us. So we have an optimizer, we have a loss, we just iterate over the dataset multiple times, and we update our optimizer based on the loss. The evaluation is also very simple. We set the model to evaluation mode, collect a prediction, and compare them with the original data. Nothing weird, nothing esoteric about this. Let's have a look at how something like this behaves on a real scenario. So I'm going to be using a graph data set, which is called Cora. It's a citation network. I'll give you a few numbers about it in a second. It essentially represents multiple papers. We're talking about 3,000 papers, 2,700 papers that are connected with each other via citations. The number of connections is about 5,400. And all of these papers are part of one of 7 categories, depending on the type of publication. The task is trying to predict what category each paper belongs to. And each node, so each paper, also contains a bag of words set of features, about 1,400 features. Initially, I wanted to actually have a live coding session about this, because it's, if you look at the numbers, we're not talking about a huge amount of data. In the end, I decided not to, and you'll see why in a second. So the way the labels are distributed, yeah, as I mentioned, there are actually, there's a mistake here. It should be 70 topics, not 7. And each node represented by a paper. Each paper is represented by a node. Sorry about that. So the main reason why I don't have a live coding session, the code is with the repository. So if you want to have a look at it and run it, please go ahead. But I'm not running it here because when I did that first time, the gradient boosting classifier took a little bit longer than I would have liked. It took almost 4 hours. And that was on a more powerful laptop than this, so I'm not even going to try here. Whereas the graph network actually took less than 30 seconds. So good start. And then when we look at the metrics, the graph network actually did a lot better by a considerable margin. And just to give you some numbers here, I used the gradient boosting classifier from scikit-learn, nothing too fancy. I gave it 100 estimators because I wanted to be a bit thorough. So I wasn't trying to bias the ground towards the convolutional network, which is exactly what you've seen earlier in the code. Exactly that. And as you can see from the results, the graph network worked a lot better, right? And the main reason is the fact that the gradient boosting didn't take into account how each paper cite each other. It was just using the backwards content of the papers, which is considerably better than random guessing, but it's still way worse than what the convolutional network could do. So I will try to be a bit quick here about a few things. We're coming to the end. So one major positive or major pros of graph neural network is the fact that they capture not just the data and the tabular representation of values, but also relationship. And I have used these successfully in a lot of situations in which relationships are key, like for example, fraud detection, or I use them quite a lot in the clinical domain, try to understand what patterns will emerge over time for disease prediction and for risk prediction. And most data in the real world is relational after all. So like having a good understanding of how relations impact the final outcome sometimes is very important. It can be used, and I have used it in building recommender systems, which can be very helpful in understanding not just the direct behavior and transactional behavior of the users, but also how they aggregate together, what kind of communities exist, what kind of similarities you have. Excuse me. And as I mentioned, it's fairly used in molecular biology as well these days. Okay, we're coming to the end. I'm actually going to open it up for questions, so that I hope there are a few.
Okay. Sorry. Yes, there are coming right now. Okay. So why Cora dataset edges are undirected? Paper X cites paper Y doesn't look like a symmetric relation.
Yeah. Well, in this case, the edges are in fact directed, not undirected. It is the type of edge is paper cites paper, so it starts from a source and it ends up in a destination.
Okay. And another one is, how can you handle horizontal data scaling with graph data?
Ooh, this is interesting, actually. This is one of the major issues that you have building graph data and representing it. There are a few tools that allow you to do that. I have to say one of the major disadvantages of graph data and graph databases in general tends to be cost. There are some tools that are insanely good, insanely fast, and they can scale up really well. When I was working in a previous company, we actually had a production database, graph database, that we were using to run analysis and train machine learning model, and it scaled easily to well over 1 billion nodes and God knows how many billion edges. And it was still performing really well. The main issue there, as I mentioned, is finding the right tool, the right representation, getting the right type of schema for representing your data is key. Similarly to a relational database, you can scale a lot better if you represent your data in a proper way. Yeah, that would be my take on it.
Okay. Another one, how large can the dataset be for a GCN, and how do you deal with supernodes?
Okay. I never had to directly deal with supernodes, so we can, like, if you were curious about that, we can have a chat offline, perhaps. In terms of how large the dataset can be, it's really limited by your time and compute. It's very similar to what you would find using conventional networks. In my case, running it on my laptop for 4 hours was fine. If it had run for a month on my laptop, it would not have been fine. But in some cases, and depending on your goal and type of model you're building, a few days, few weeks even, so you could probably scale to up to a few gigabytes or terabytes even. Depends on your hardware.
Okay. Another one. Do you do any data augmentation with training with GCN? Like, for example, shuffling nodes around, similarly to how you may shift, rotate an image in a regular CNN?
You can do something like that. Well, there's definitely a lot of data pre-processing that goes into it, mostly about standardization of the data. Clearly, GCN being a type of neural network benefits from having some type of standard representation of the data. Not as much as some other models, but still might be beneficial. In terms of data augmentation, it tends to be not as important, at least not in my experience. There are techniques, but to be honest, over the last 10 years, I probably used them once. So I can't even say I'm an expert at that because I used them once.
So another one is, can you combine several GCN in an ensemble method?
Sure.
Why not?
Definitely.
You can assemble anything.
I'm actually a big fan of ensembling different models together, especially if they are all looking at different types of features and different type of patterns. You should be careful to make sure that you're not ensembling two things that are looking at the same type of features, though, because it's a bit redundant.
Okay, another one. We have plenty of time for questions. Thank you for you ended
I tried
early.
to power through it.
I don't get the intuition behind graphs neural network. With normal neural networks, we are learning vector embeddings when we have each point in n-dimensional space and we can compare. What's the situation in graphs?
Well, the analogous here is that instead of learning data points embeddings, we are learning node embeddings or graph embeddings, or even edges embedding. So you're trying to represent in a concise way that still carries lots of information, either the entities you're trying to model, how they're connected to each other, or the whole network. I think it's a very similar type of result in the end. Then you can use those embeddings to generate more insights as to how your entities are behaving.
Okay, other questions are coming, so thank you. What are the computational or infrastructure considerations when you're scaling GNNs to millions of nodes and edges in a real-world banking scenario? Context, sorry. That was
a real-world banking scenario?
Real-world banking context.
Banking context, okay.
The wording. Yes.
Well, the considerations would be the same that you have in other analogous situations with regular conventional models. So data representation tends to be key. You want to have fast retrieval times, fast operation times. Aside from that, some tools are beneficial in terms of retrieving the data and representing the data for optimizing for how relationships are represented. I mentioned that there are some graph databases. I can give a couple of names. They're publicly available paid products. So some of these would be, like, for example, Neo4j, which is probably one of the oldest players in the market. We had lots of success in the past using Tiger Graph, which is a little less user-friendly, but considerably faster and considerably more expensive as well. That actually really allowed us to perform very deep analytics on 1 billion+ nodes very quickly. So we're talking retrieving hundreds of thousands of nodes in less than a couple of minutes through complex relationships analysis.
Yeah, there is a question related to that. How come the graph-based model learns so much faster than the gradient boost classifier? What's the core point behind that?
Well, the main point is that gradient boosting is a great type of model family of algorithm, but it's not the most efficient I know. So the problem with gradient boosting is that, especially if you give it a lot of trees, it learns sequentially, right? Whereas graph neural network, especially if you have a decent CPU, ideally the GPU, it's just matrix operation, so it's very quick. And the optimization for gradient boosting in particular is way far from being as fast. So that's, in this case, it's mostly because of the algorithm. I could have chosen something like random forest, which could be easily parallelized, and it would have been a lot faster, but it also tends to be not as good in terms of tabular data prediction in most cases that I've seen. So I tried to give the challenger model a bit more of an edge in this case, but still.
Okay, they are keep coming. Okay, great. But we have you are over time, so last one.
Okay.
Does it make sense to apply GNN on embeddings derived from another network? For example, a convolutional neural network or any other encoder for images?
This is a deep question. I don't think I can answer it. I need to think about it for a second. Does it make sense? I would say it depends on how you look at the embeddings and create them. Because here you're looking at node attributes and how they're linked to other nodes. What do these embeddings that you bring in as input represent? Because if they are just node embedding, it might make sense in some ways because it's essentially a rehash of what you've done, or what you would do within the GCN. So you're learning embeddings from the neighbors. So mathematically, in my head, it does make sense. I don't know if it has a physical meaning. I would have to think a little bit more about that.
Yeah, I wonder how you get out the value out of it. How do you build the graph out of the embeddings? So anyway, we're over time. So thank you very much, Pietro.
Thank you. Thank you.
Of course, since you had so many questions, you can continue and ask him, but outside of this room. Thank you very much.
Thank you.
È stato un piacere. Actually, I think we can start.
Yeah, awesome.
Okay. So it's a pleasure to introduce Archana.
Yes.
Okay. Archana was previously a data scientist, an AI engineer, and AI researcher. Currently board of director at Women in Machine Learning and developer advocate at Aleph Alpha.
Yes.
Okay. If you are interested in her work, you can go on YouTube and search for Introduction to LLM. There is a series, 6 episodes, I think.
Yeah.
Very interesting. So, big round of applause.
Oh,
thank you
so much. Yeah, thank you. Yeah, thank you so much for coming over and listening to this very opinionated talk. And I have a Mentimeter here, so my hope is that we can make it much more interactive, and you folks feel like I'm not droning on, and you have a chance to also use the QR code and go on to the quizzes. Awesome. Just need to scan the QR code, and you should get access to Mentimeter, hopefully. Awesome. I see a few folks here already. I can wait around for another couple of minutes. So yeah, just to give a quick introduction, I'm going to be talking about why AI-first architecture could be sort of our big engineering crisis. I think everyone is vibe coding at the moment. And what does that mean for our infrastructure going forward, and especially our Python ecosystem, right? And most of my background has been in AI engineering, as said, and I've been a data scientist, and primarily very pre-GPT time. So really used libraries from scratch and really used all of this to build models. But now everyone is prompting. So then what exactly happens going forward, right? So that's what my talk is going to be about. I'm going to give a few situations and sort of try to understand what you folks feel, and then also going to give a few scenarios of people or companies that have already integrated AI at every stage, and what does that look like for them, right? Where are they running into issues, and maybe you're running into the same issues you don't know yet, or maybe you will in the future, right? So yeah, that's what the talk is about, and I gave a bit of a background about me, but mostly I've worked with AI engineering and obviously worked in the Python ecosystem as well. I help out at Python Software Foundation, and most of my roles have now been very community related. Okay, I'm going to start with a question to capture your, attention. So over here, let us say there's a company that needs to build a sophisticated booking system for a cruise line that handles multiple ships, cabin types, customer profiles, and payment processing, right? Maybe you as an engineer or a product manager or a project manager, what do you think best represents how you would handle this in a traditional software architectures? Would you actually hire a team of 30 developers to simultaneously code all features, then integrate it in the end? Would you start coding immediately based on a rough outline and adjust this as you get customer feedback? Will you actually follow a sequential process of requirement gathering, architectural design, component design, implement testing, and deployment? Or would you actually purchase an AI code generator and have it build the entire system for you? So what do you think you would choose for this particular scenario? And again, I don't know what you're answering, so don't worry, no judgments here. The idea is to just get a grasp of what folks feel is really happening in the background, or what would they do in such a situation, and try and explain where, AI is plugged in, and possibly also explain where I see failures already happening and where it might happen in the future. So yeah, that's amazing. A lot of folks already say they're going to follow a sequential process of requirement gathering. So I put up this very, messy flowchart here, but what it basically goes through is a traditional software engineering architecture, right? You start off by doing requirement gathering, where you identify, you understand user requirements, then system requirements, and then feasibility studies, and then you would ideally move on to architecture design, right? High-level system design, component identification, technology stack selection, etc. And then obviously come up with a detailed design on component-level design, algorithm design, and then data structure design. So all of that is also handled. And towards the end, you would always have an implementation or coding, and then testing, and then actually like deployment, and then maintenance and evolution. So this is something that traditionally all software architectures will follow in one way or the other. Even if you miss out on certain parts or replace certain parts, this is what it looks like. Right, and now coming towards like where you think AI will be used in this pipeline, right? Like, and especially like a lot of libraries will be used in this pipeline or replaced in this pipeline. So let us look at this another question here. Your product manager wants to add a recommendation engine to your e-commerce platform that suggests products based on browsing history, purchase patterns, and seasonal trends. Would you use the traditional waterfall approach, but with AI tools to accelerate coding? Would you actually put an AI system at the center of the cyclic process that I put it like over there, the flowchart where it generates? Would you replace all human developers with AI and eliminate the phase entirely? Would you generate the entire code base at once using AI and then deploy it without testing? So which one would you use? Yeah. So again, feel free to put any answers in. I have literally no clue who's adding what. And the idea behind it is just to understand where you're coming from and what you choose. Yeah, awesome. So again, like a lot of us might be coming from traditional backgrounds or have been a software engineer for a long time, and we would end up using the first approach, which is really good, right? Like this is exactly what we want. And so now let us look at how AI-first software engineering architecture really looks like. So let's start from the top, right? So let's look at requirements co-creation, right? That is where you'll ideally use AI, maybe a product manager does, to collaboratively generate requirements, and AI sort of validates those requirements for consistency, completeness, and maybe suggests like, or identifies potential issues. And then you can do like architectural exploration as well to an extent. You can ask like AI, okay, can you generate multiple architecture options? Can you evaluate and refine them? And then you can, what we do already, vibe coding, right? Like AI generates code for certain parts of the architectural decisions, and we look at what the code it generated, and sometimes it's extremely bad, and sometimes it's good enough to be deployed. So yeah, we go and improve the codes that generated. And then when you look towards the end of the pipeline here, it is like continuous verification, where maybe AI can be used for creating tests and identifying edge cases. And AI can also be used to analyze code for potential issues. And then adaptive deployment, maybe AI comes out with your deployment configurations, or AI monitors the performance and suggests like optimizations. And eventually you want it to do like some kind of proactive evolution, right? Like where it analyzes the system for improvement opportunities. So this is something that maybe ideally would happen in a very ideal world where AI, helps out with every step and does it perfectly, right? But what really happens out there, right? I have, unfortunately, another question as well. I hope I haven't bored you. And I know I've been giving a lot of diagrams, so the hope is that you can see this and think about it. So let us say a major retailer sort of adopted a AI-first architecture for the inventory system. 3 months after deployment, they discover the system occasionally processes returns incorrectly, causing customer complaints and inventory discrepancies. So not the same domain, but I worked with a company or consulted a company that has deployed something and then later on found out that there were issues. So where do you think the issue could have come with? Or where do you think the failure likely originated? Did it originate at the AI requirements, where there was a co-creation of maybe AI misunderstood the business rules? Was it in implementation, collaboration, like where AI generated code with like subtle logical errors? Or was it in continuous verification, where AI generated tests which failed to catch like edge cases? Or was it at a proactive evolution, where AI made like unauthorized changes to the system? Again, the idea here is like no perfect answers, but something to think about as to what happens when these things actually get deployed. Awesome. So yeah, most folks here are absolutely right. So AI-generated tests actually fail to catch edge cases. So this is something that I've actually seen, is that AI tends to hallucinate, or most LLMs tend to hallucinate, and that actually happens in the edge cases. It doesn't happen in the test set you generate, but it will happen in the test set that it hasn't understood, or like cases that it hasn't seen already in its training data, right? And now comes, like, that was one point where you understood that there were edge case problems, but when you look at the architecture as a whole, and again, this is something that I have generated and like sort of gone through in my head, I see like various points where failure to sort of occur through the pipeline, right? The first is hallucination failures, right? With the requirement co-creation. So let us say that means maybe AI is inventing non-existing requirements. And then let us say like at architectural exploration, there's pattern misapplication. Maybe AI is suggesting inappropriate pattern architectural patterns, or AI is generating code with subtle logical flaws, and then AI is failing to test critical edge cases, which is exactly what happened with this company. And AI is making inefficient deployment decisions, and AI is suggesting sort of these changes, which is not good, or like introducing changes that doesn't really help. So another situation that I've actually found happen is, like, let us say this particular case, right? This particular company used actually AI to build like an authentication system for their new healthcare application. And during like a security audit, a serious vulnerability was discovered, which basically exposed patient code, right? So what do you think happened, right? A, did it deliberately create malicious backdoors inserted by AI? Or B, was it outdated security practices copied from like sort of the training data? C, was it a complete absence of any authentication checks? Or D, was it encryption algorithms that are too strong and slow down the system? I know this is a bit of a difficult question, but yeah. So again, like no right answers, no wrong answers. The point here is to understand that, oh, this happened to a company, and then like, what did they do? Where did they find the issue that came out with? Exactly. So AI actually generated, was looking at outdated practices, and this happens often, right? Because you realize that these LLMs, like if you take like if your, I guess, architecture or your model that you're using for deployment is using GPT-4, means the training data for GPT-4 is what it's looking back at, right? And you are just doing an API call, and you don't know that GPT-4 actually can or cannot look at newer data. So at the same time, you end up like using parts of the code which are pretty outdated. This includes security vulnerabilities, which people don't think about when they are like vibe coding or putting things out there very quickly, right? So this is a really nice company's like, I would say, use case around where they found AI failure points to come in. And this is taken from Gergely's article on AI engineering in the real world. He took it out like a couple months ago. And so there's this person called Ross McNain from Wordsmith, who identified that the biggest challenge for developers transitioning to AI work was the fact that AI actually produces a lot of varying results from the same input, right? And that is something that is going to keep happening with vibe coding, right? Like every time you ask it to generate like even a website, it's always generating something different. And that is something they also found out. And the way that they approached it was, oh, can you have good evaluation frameworks to sort of assess the AI output quality? Can you actually have like domain-specific quality metrics, right? Because if you have like general or generic quality metrics, you know the AI will tend to pass that anyway. And you need to build systems that improve these feedback loops as like seen by the chatbot implementation, or like creating these approved answers for knowledge bases when deterministic responses are required. And so with this case, they clearly had an issue with pattern misapplication, sort of AI suggesting inappropriate architectural patterns. And there's another interesting case study that Gergely pointed out, which was a fact about this like Data Solutions International that sort of showcased how AI vendors oftentimes propose unnecessarily complex architectures. I don't know if your companies have done that already, tried outsourcing some form of AI to a third-party company. And what happens oftentimes is that they will take 6 to 9 months to do something similar, and it actually costs way more than actually building the infrastructure in-house. And I've actually talked to a lot of companies that are jumping on the wagon now. They're like, oh, we need to do generative AI, because if we don't do it, we are not going to get like our next round of funding, or maybe we won't be labeled as an AI-first company. But what does that mean? Like, does it mean that you couldn't do the same thing with a few Python libraries in-house, right? So those are the questions that you should be asking when a company jumps into, oh, AI-first architecture or implementing these generative AI application. Yeah. I have another question here as I go forward. And again, it's just to get your attention, so don't worry. The idea behind is to just come up with good situations and scenarios which make sense. So let us say your team is building an AI application that needs to perform various types of tasks, right? Like code generation, summarization of legal documents, and real-time content generation for user interface. You're debating whether to standardize on a single AI model or use specialized multiple models. I think this is, again, a very interesting way to look at how we are dealing with things. I think people forget that most LLMs out there are very general purpose, right? They were trained on enormous amount of internet data, which means when you actually apply these general purpose models to a specific scenario, they fail. Like I've consulted this one company which worked on marine industry, and they were trying to slap GPT-4 API to help them, generate responses or write emails. They had a very specific use case for writing emails. But that's when I realized, like, you really can't use GPT-4 API because it won't understand a lot of terminologies that are very, very specific to marine industry, right? And that's where a lot of teams go wrong as well. You look at this model, which is ever so knowing and obviously has like a lot of data that it has learned from, and you're like, yeah, now it will answer every question that the customer puts out as in the customer support, right? But that's not necessarily true. It might actually not know the domain that you're going after. So this particular scenario is also like that. What would you do if you were in this place, right? Would you use like a single powerful model like GPT for all tasks to sort of simplify integration and maintenance? Would you build separate applications for each task type with different applications? Or would you create like an abstraction layer that allows you to use different AI models optimized for each specific task? Or would you outsource each AI capability to third-party vendors? And I know like I already gave like the answer out for this, but great to see people are using other responses. This means you folks are still awake. So that's a win. So yeah, I would say like, yeah, actually creating an abstraction layer works the best. And also the fact that you can actually route to different LLM models. So right now, there's a new concept called judges and routers. I don't know how much you are familiar with it. It's relatively new, but what it does is it asks like a model to sit in between and actually evaluate whether your prompt that you send to this model should be sent to a smaller model that could perhaps like answer a simple question like, what's the capital of France? You don't need to probably prompt a big LLM like GPT-4, right? You could get away with prompting a small LLM as well. And that's what happens here is that when you create this abstraction layer, you're trying to get to different models that are specialized to do certain tasks. For example, I don't know if you've realized, like Claude actually generates better coding. Like it's great for vibe coding, at least for me, as compared to GPT-4. And there's certain studies that actually show that as well. So let us say a customer is asking something very specific to the code, or you get like a question which is very specific to a code. It makes more sense to send it to a model like Claude because it can actually understand code better than, let us say, Llama 7B, right? And the small abstraction that you actually end up creating will make sure that your application is much more sustainable in the long run. Because these general purpose models will keep continuing to be general purpose, but that doesn't mean it is perfect for everything you're looking out there. I'm going to move ahead because I know I've asked a lot of questions already and get to the most important part, which is like, which kind of open source libraries that I think are under threat from AI or what is happening around us, but especially vibe coding and sort of prompting GPTs, right? And so let us say this question, right? Which category or like which type of open source library do you think has a higher chance of being replaced by LLMs? So again, like a very easy question out there and no right or wrong answers. It's a very opinionated talk, so feel free to disagree with me at any point and go like, no, I don't think it's going to happen. It's completely fine too. Yeah, so I think a lot of people got the right answer. According to me, I do think it's a lot of interface and convenience libraries. Like, for example, there's a library that I'll talk about, but there's a library that helps you create slugs out of your text, right? It's called Slugify. It's a Python library. So what happens is you could just create the slug by prompting GPT, right? You could send it to GPT and be like, hey, GPT, can you actually create like a slug out of it? And most teams are now doing that. They aren't going and searching Stack Overflow anymore to figure out the best Python library out there. They're already prompting GPT, right? And which I think is not great, and for several reasons, but that is definitely happening already. So this is one library, as I talked about. So if you see here on the code on your left-hand side, that's what is required to actually turn the text into slug. But you see on the one on the right, that is what is needed to actually convert it using GPT-4. You have to write a whole prompt to ask it to take care of every edge case and also like create a slug out of it, right? So this is happening already. And that is why I believe a lot of these Python libraries are vulnerable to LLM replacement. For example, string manipulation library, data formatting libraries, and simple web API and like web and API utilities. So something as simple as tabulate, humanize, making number, dates, and file size more readable. Or over here, I also had this emoji, converting emoji codes and Unicode representations. And I don't think we realize the Python ecosystem is so large, and it's been held by a lot of open source developers that worked really hard to build a lot of these, right? Some of them might be directly used by LLMs as well. Like, for example, if you ask an LLM to generate a plot, right, or a graph, it will use matplotlib, which is good, right? But at the same time, we know for a fact that it's using these Python libraries sometimes, but mostly it isn't. And the space where it's actually not using Python libraries has the highest chance to hallucinate, right? So you put it out for production, and there's a good chance, because you just prompted it, you never knew the edge cases. And it ended up missing it. But you have to realize when you actually use these Python libraries, they have been built for a lot of years thinking about those edge cases in mind. So yeah, I will go ahead because I don't want to bore you with too many questions. But yeah, so I actually like generated like this very like quick website. You can also scan it over here if you want to like check it out. OK. So the idea behind this website and why I put it out there is because let us say you were using Slugify instead of, or let us say you were using GPT to prompt and remove the slug, right? Or like generate the slug from your text, right? What happens is when you put it into production, there's going to be 1 million tokens that's going to take over time, right? As your users increase. So this means there's going to be cost for using GPT-4o, which we don't realize right now because everyone is like, oh, these models are very cheap. But I've also done like good analysis, and I'll show that later. But there's actual proof that there's a race to the bottom with how cheap these models are. So like, wouldn't it make sense to actually use a Python library instead, which is like free of cost? So this is almost like an ironic calculator I created. But the idea behind it is if you were to use like talk about the libraries, and you were talking about like, amount of tokens per, yeah. And let us say you were also giving like average tokens per second and the AI model, you could calculate like the risk cost. So the idea behind it is, as the number of tokens keep increasing. This means like every time a user is asking something, you are actually pinging, GPT-4. You're pinging a lot of different models to get your answer, right? So over time, this graph is almost exponential. It keeps increasing for you because the cost will keep increasing because you actually used prompts instead of using the Python libraries directly. So this is what this basically goes through, and it's just like a way for people to realize that, yeah, you really cannot use GPT-4o or prompt these models. And happy to have you like take a look and see if there are like ways to improve it. Yeah. So I really think there's a huge reason why we need to preserve open source in the ecosystem or in the age of AI. Because right now, a lot of new developers and new software engineers are probably not thinking about these open source libraries at all, which were probably maintained and built by really, like people who wanted to give back to the community, right? And I think there's a bigger need to start preserving these libraries and sort of like raising the point that, oh yeah, please don't stop doing prompt and pray. right? And I also like put up like these, and if you look at like, ways to sort of understand, okay, now I still want to build, Python libraries, right? But how do I end up doing that? I want to still build Python libraries in the age of AI. So for that, I actually like put up this nice pipeline diagram that goes over like, the various parts of how like machine learning models are built. Probably you already know that. And I think certain libraries that are wrapped around these AI pipelines will survive, right? So for example, if you were looking at the data layer, you could be using something like a vector database layer, like for example, PyCon or Llama Index or LangChain for like orchestration. So that I think will still survive because that is around AI pipelines, right? And the same for like prompt layers, right? So I am gonna shamelessly plug here, but I actually have been working on a open source libraries that helps people understand how to prompt better because a lot of people are very verbose with the way and they use please and thank yous to model, which they don't need to. And I said, okay, fine, is there a way to actually reduce tokens? So I actually generated like a Python library that is sort of wrapped around or like just works on the prompt layer. And then obviously for monitoring layer as well, I don't know if you already know that, there are like a lot of ways to evaluate models. There's Langfuse, there's Ragas. These Python libraries are again very sustainable because they're helping you evaluate prompts. They're helping you make sure that these pipelines survive over time. So yeah, I have another question here, and sorry for that again. It's a way to just get your attention here. So yeah, so let us say it's a health corp which sort of got hit by a regulatory audit, and the AI diagnostic system gave wrong cancer screening results to more than 200 plus patients. I mean, it can still happen. And the FDA is investigating and insurance won't cover claims and they are facing close to 2 million in lawsuit, right? And let us say there's an emergency board meeting and they say, oh, we need to fix this or we are bankrupt. So which tools do you really think they will need to absolutely fix something like this? Will they need like requests, like API calls to patient database? Would they need Ragas that helps you sort of evaluate LLM responses and reduces hallucination? Will they help you, will it help to ping matplotlib or JSON, right? And this is a pretty straightforward answer out here. But the idea and the hope that I have from a question like this is the fact that, again, like AI libraries or like Python libraries can still be built around AI pipelines, which will still be very useful and still will be maintained by a huge number of people. And I think that is another way to survive what is happening and what is coming forward, is to adapt these libraries and make sure they are fixated somewhere in the AI pipeline. Yeah, so awesome. So you already figured out its answer B, which is Ragas, which helps you sort of evaluate LLM responses and reduce hallucination. So yeah, and another thing that I would say, and again, the talk here is purely like, it's not a product talk, it's not a talk to, advertise something. I'm doing this talk to sort of put out there that it's important to do open source work, and it's important to have like the symbiotic relationship even in the age of AI, right? And that is what my hope is here with preserving it. And I've also put up an open source learning hub. You can also submit your own open source, courses or anything else that really helps people understand the value of open source, and this can be found in the QR code there. Other ways that I think organizations can, what can they really do to make sure that if they support open source work, is like you can conduct like a OSS inventory, sort of identify which open source components are critical for your infrastructure, establish contribution guidelines, and allocate support resources. We still need organizations to really support open source work, which is going to decline, so we need more people to sort of advocate for it. And yeah, so again, like open source ecosystem represents decades of collaborative human knowledge that benefits all of software development, which is, again, very important to wherever we are going next. And I think like the most successful organizations will recognize that it's just not about altruism. It's about ensuring that the foundation upon which all the software innovation still depends on like this, strong and vibrant future generations of developers, right? Even though they might say that, yeah, like, LLMs will replace developers, or we have like a possibility, or like even like, executives on top might think that, I still do believe that there's a space where both can coexist, and most importantly, open source can still survive. OK, awesome. I will move ahead. And yeah, I think like, yeah, this actually is a good question. OK, so this question is very interesting because I talk about this pricing paradox, right? What happens is, let us say your startup was sort of built on a product with an AI agent, and there's a cost of around like $20 a month, right? That's what you see when you prompt GPT-4, or you're like, so cheap per token. Why can't I just use this, right? And the AI agent sort of handles customer support, generates content, and monitors your system. 6 months later, you receive an email. Due to increased operational costs, our pricing will change to $200 per month. FYI, Claude just did that. So, and there's usage-based pricing starting next month, right? So what fundamental risk do you think such a scenario illustrates about AI-first architecture? Is it A, risk of AI models becoming outdated too quickly? Is it B, the dependency of subsidized AI services that will eventually need to change sustainable pricing? Is it C, the challenge of training employees to use AI tools effectively? Or is it D, keeping up with the rapidly changing AI technology? And again, the answers, there doesn't need to be right or wrong, which I think a lot of people already got. So yeah, exactly. So I think like there is a bit of a pricing paradox. And I think like Gurgly, again, has a great tweet around it. But what we need to realize is right now, a lot of tools are subsidized. Like I have been an AI engineer for quite some time, and I know like pre-GPT, when we trained models from scratch, when we trained them for like particular use cases like deep neural networks, it actually costed a lot, right? And the fact that they are giving you such large language models for $20 a month means that there is a catch, right? And I think like we are sort of ignoring that right now and going ahead and creating a lot of applications that are dependent on this, but eventually we will start to see the cracks. And yeah, so firstly, like a lot of things, a lot of companies that I talk to, they often go like, yeah, our architecture is already dependent on GPT-4 Mini, right? We can't change it right now. So that's another thing that will happen eventually, is that people will start building all of their technologies around LLMs, right? And architectural dependencies are sticky, because once you build it, there's little to no change that you'll actually do in the whole pipeline. And integration complexity compounds. That's another thing. So token cost is always an exponential cost, right? As your users increase, the amount of tokens you put is actually exponential. So let us say you were talking to an LLM or a GPT, right? When you start the conversation, it might start with one question. But every time you ask it the next question, it's basically taking all the chats that you talked to it previously into the model as well, right? And it's having that context. So what does context mean here? It's a multiplication factor of your tokens. And in some ways, your feature dependency creates a lock-in. Applications are built around provider-specific capabilities, and you may not have equivalent alternatives. So yeah, this is like towards the end. I also have a library rescue network here that I quickly vibe coded. And the idea behind this is that you can actually like submit, you can submit any Python library that you think is under risk, and I'll try to promote it and put it up on the website, and we can hopefully get more people involved, and they can possibly help out with making sure that such libraries sustain, but most importantly, if they can be used in some parts of the AI pipeline, maybe that's a way to sustain it, and we elevate this problem that is happening. Yeah, that's pretty much it. I know I have only 5 to 10 minutes remaining, so I'll go ahead and ask folks for questions. And feel free to ask me any questions. I guess in PyLadies Berlin, they have like this rule of no stupid questions. Like no question is stupid enough to not be asked. So please go ahead and ask me questions. Yeah.
Thank you very much. So the questions, please ask them on Slido. I'm checking now.
You can also raise your hands and ask. We are a small group.
Yes,
so
if you want. We are not so many, so we can also ask directly.
Yeah, go ahead.
Sorry.
Thank you for an amazing presentation. My question is, as a ML engineer, where would you encourage me to invest my learning, like, and skill focuses?
Yeah, that's a good question. I think like there has to be a balance in which we sort of learn and understand machine learning models. And I think like a lot of how we learn machine learning models has to still come from traditional learning instead of just learning how LLMs were, put together or how tokenizers were built. I think the learning has to still be very rudimentary. And when you do rudimentary learning, you're in any way you will learn important parts of the Python libraries used to create that, right? Instead of learning just about LLMs. And I think like the learning definitely has to change for that. But yeah, great question. Thank you so much, Jessica.
Okay, other questions?
It's okay.
I see no on Slido. Yes,
Yeah.
Sorry.
So, don't you think that with LLMs getting commoditized, the price is going to go down, actually, not up, as you said in the last slide?
Yeah, I think like the prices right now are like heavily subsidized, right? They're like trying to compete with each other on the prices. But if you notice, like better models are still priced much more than models that are way smaller, right? And let us say you were trying to build like a whole infrastructure around these models, right? Or like trying to build an application. In the end, you would want to use the best model that's out there, right? So let us say it's O3 or it's like, the latest Claude model. It will still be priced way higher than a GPT-4o mini, right? And that itself will start showing up in your like wallet, right? And you won't realize it now, like once you deploy like a MVP, but once you put it out there and you want like thousands of people or 100,000 people to actually ping it, the costs slowly rise, right? And we know for a fact, like there's another like discussion that I was having recently, like a lot of these chips that are made, right? Like we know there's Moore's law that states that, okay, chips will keep reducing every time like 2x in the size, right? And that means like you can fit more AI models in the chips, like at least on paper. But we know for a fact that even if chips reduce size every year, your models are still getting way bigger at a much more bigger rate than the chips are getting smaller. So eventually we will come to this point where, it might seem it's subsidized for now, but like let us take Uber or something, right? The way that Uber did is like they monopolized the market and then they increased the prices. And I think that's what these companies are doing right now, especially big LLM providers. They're just trying to reach market sizes. Yeah.
Okay, thank you. Other questions? So I have one,
yeah, sure.
which is, so I think this points out how much is important to have open source models and open weight models.
Yeah.
So I think it's also important to have community efforts to build models that can be
Yes, absolutely. And I think like modeling itself is just not a single API call, which I think a lot of people forget, is that models are really built to do specific tasks. They are not built to be general purpose. And the more we try to build and try making these models all knowing, the more we're going to see places where it fails. So I think it's very important that we actually think about much more community effort building, testing, and understanding these models. And that can only happen if we push for the fact that there shouldn't be closed source models in the first place. And if they're open source models, we're testing them for the right situations, and they just don't come out and go like, oh, wow, our model cleared like a law exam, right? They cleared a law exam, but we also know for a fact that the law exam could have been in the training data, right? So those discrepancies won't come out until we do the testing and until we push for it. And I think the community sort of forgets that it's a bigger force as well. Yeah. But yeah, thank you so much.
Anything else? Okay.
Yeah.
We have time, so.
I will ask her questions all day. I think so. I guess what I was thinking about is, like, you mentioned about new developers being less aware, maybe, of open source, and I think that's a very valid point. So I'm wondering, like, how we also engage people back into open source, considering I think we went through a period also where open source became trendy, but also part of big companies.
Yeah.
What's your thoughts there?
Yeah, that's a really good question. I think like companies again play a huge role in making sure open source actually stays alive. So this means like if you're part of an engineering team, you can actually advocate for more open source tooling. And you can be like, yeah, we can use GPT 4.0 and it looks like an easy solution today, but it's not an easy solution in the long term. So I think like there will be people who would have to advocate for change. That's exactly what happened with open source before, and why like Linux and stuff like survived in the age of whatever is happening. So yeah, it's a much more community concerted effort, and I think like it's important that engineers recognize that, which is why I'm doing these talks in the hope that I can push like even 5 people forward today. Yeah.
Okay. Anyone? We have 5 minutes.
It's okay. Yeah, I think everyone also needs to go for the coffee break, so we might as well leave early, yeah.
So, I think
Yeah.
we're good. Thank you very much.
Thank you so much for attending. Thank you.
And I mean, I don't know, the voice is like, if I shut up.
Attenzione, attenzione, è stato trovato un portafogli con...
Yeah, that works. All right, so I would like to introduce the second keynotes of the day and of this edition of PyCon Italia. Alessandro is a friend, former colleague, and of course is an amazing speaker, and he's gonna talk about composable data systems. So thanks, Alessandro.
Thank you, Ernesto. First of all, I absolutely know that after this keynote, there is the PyDrinks. So there are only two possible outcomes of this talk. One, you tell your friends that this was a good talk. The other is you complain all time that it was a bad talk. But then there is the third option, which I'm the one that I hope for, which is that everyone here is so tired that they won't do anything else than sleeping, and I can say anything, and they will all be happy. That being said, so a little introduction about who I am. I've been contributing to open source projects for a while at this point, and some of those open source projects are involved in the technologies that I'm going to discuss here, like the arrow data format, the substrate query format, and Orbital, or other open source projects that I worked on over the course of the year. During my career, I worked both in management and in pure engineering sides, and I'm the author of some Python-related books themselves. But today, I'm here to talk to you about composable data systems. And you might be wondering what they are. By definition, by definition of the composable word itself, it means that they are systems that can be built by combining multiple different components and that are designed from scratch based on open standards that allow these components to interact and work together. Modularity, which means that I can replace individual components. And separation of concerns, which means that every component has only one duty, one clear role, and everything else is not its problem. The coordination across those components happens via those open standards that allow them to communicate. So there are two possible outcomes when you work with composable data systems. You more or less understand what you're doing and you build a wonderful, strange Lego, or you try to combine components in a way they were not designed to, and I don't know what you end up with in that case. Don't come complaining to me just because I told you to use the technologies. The evolution of data systems, primarily, has been switching between two different phases over the course of years, and moving from monolithic solutions, I would say, like data warehouses, where you had something predetermined in terms of schema, where your data was consistent or in one place, your compute engine, your data, your query planner, query language, everything was in one single thing that did everything. You did not have to care too much how those things were built internally. And that also caused the problems that we all know. It was hard to scale those solutions because they were very bound together, tightly coupled. Dealing with schema when large data is involved, it's not easy, especially when the data comes from different sources that are independent and might not even allow you to easily normalize the schema before your data reaches your data warehouse. And it was very bad at unstructured data. I mean, that's not what most database and data warehouse systems were designed for. So after the data warehouse trend, if you allow me to call it that way, which lasted for a very long time, I brought from the 80s, but actually I think that we can consider that trend far before if we don't stick to the name data warehouse itself. And after the trend, we realized that scaling those systems was not easy. And so we started trying to design solutions that were a trade-off. We're still trying to be more or less monolithic. So the compute engine was still tightly coupled with your data. And we tried to relax some constraints to be able to work with big data like the schema. Most of those systems designed in this era started to consider the schema an afterthought. And many of those systems moved a bit away from the ACID guarantees to try to make easier to scale the system themselves. So we started having NoSQL database like MongoDB graph database or things that actually they existed far before, but they became more mainstream. The problem with those technologies became that they were still custom designed in the sense that they required your application to start having much more knowledge about your data system because it had to take over some responsibilities that previously were on your data system, on your data storage database management system. And there was a lock-in, like people that went for MongoDB had a very hard time moving away from it because not much was compatible with the other existing systems, or people that went to Hadoop, when you end up with a big amount of data there, it was not easy to move to a different technology. It required a significant amount of effort. So building on top of these foundations, people started to try to reintroduce some of the things that they actually dropped out previously. They said, okay, well, actually it was helpful to be able to write SQL instead of some strange language that I have to learn case by case depending on the database that I'm using, or design everything in terms of MapReduce. It's not exactly the way a human thinks. And so solutions like Spark were born trying to introduce back query via SQL, via data frame, that were still fairly easy to scale compared to the past, that were fast enough, maybe not as fast as other competitors, but that were fast enough that it made sense to use them. But they still were very complex to maintain, very complex to tune, scale, and they were, like in the case of Spark, memory angry. I'm so memory angry, actually. But that being said, the next step has been more or less in the late 2010 to move to the concept of data lakes, where, again, we moved a little bit away from the previous concept of having normalized data, structured data, and as big data became more and more the norm, so it's no longer big, it's just data. We felt that there was the need to have solutions that were very easy to scale in terms of both computing power and storage. So the data lake concept more or less moved in the direction where I could aggregate data from wherever I wanted, and I could scale my store in an easy way, and I could scale my compute engine independently from my storage. And now, again, we found that, okay, but actually having a schema was not such a bad idea. So let's go back to schema again. Let's go back to transactional behaviors again. And so we are moving from data lakes to lakehouse, which is more or less enabled by table formats, like Iceberg or catalog formats in general, Duck Lake, Iceberg, and so on, that put back the consistency, transactional behavior, schema evolution that we had on past technologies, but on top of the same things we used in the past for our data lake. So it's more or less possible to take the Parquet files you already have on your data lake, build a catalog with iceberg on top of them, expose them as a consistent table, and from there on have evolution, transactional behaviors, and things like that. The problem is that it's still evolving. It's not like a standard. Anything, well, indeed, it is designed to be a standard, but anything you pick now, you have no guarantee that it will still be the standard in 5 years. We are still trying to see which technology and format emerged and sticks on long term. So what I'm trying to say is that we more or less tried to solve the problems that were in fact caused by a specific architectural choice that most data systems did in the past, which was the design as monolith. So monoliths are easy when you need to design something, especially when you need to work with data in a very fast and well-performing way. It only makes sense that your compute engine is tightly coupled to your data. It has quick access to the data. It can manage the memory in and out of the data by itself. It can work on a custom design format optimized for the specific kind of data it has to work on. All those things that are easier to implement when you are building a monolith solution. But that was also the cause of many of the problems that we had during the course of the years, like vendor and technology lock-in. If you went for a technology, it was very hard to migrate to something else. It's as easy as, like, if I picked MySQL, it was not very easy to migrate all my data to Postgres in the future. Even though they meant to be both database systems that work both on SQL, which is not a standard at all, even though people try to sell it as a standard. And it was still no really standard way to export and import data out of those systems. Every system invented more or less its own binary format. You could, in theory, export data out as SQL itself, but that had totally different problems, like size of the data and complexity of importing it back in any significantly big system. And if you nowadays speak like Spark, Snowflake, Databricks, which are amazing solutions, they do their job, absolutely work well, but good luck changing your provider if in the future your needs change. And usually those systems were complex enough that it was not always easy to run them locally and iterate quickly over your software design, experimenting and trying things, and then say, okay, things work on my machine. Now I just want to run the same exact code base at a scale without having to touch anything or care about my execution target. More or less, you had to design things based on the target system that you were on. Like, anyone who tried to build a test suite on top of like a locally running SQLite so that the test suite was quick and easy to run knows that the fact that your query runs correctly on SQLite does not mean that we will 100% return the same exact results when you run it on a Postgres database, for example. Even not for casting reasons and things like that, overflow handling in mathematics and so on. And also, it was not easy to integrate the monolith with the external features that you needed. So it's in the monolith, it's already built in, or it does not exist. Like, there are solutions like Postgres, components, extensions, plugins, foreign data formats, and all those kind of things that tried to more or less solve the problem, but they are, first of all, not pleasant to work with. They involve a certain amount of complexity. And most of the time, people ended up having to replicate the data in different systems where you maybe run a specific job. And it's not pleasant when you have to do that for petabytes of data or even hundreds of gigabytes without having to go any further than that. So the point is that monoliths are hard to scale. So the more your data becomes big, the more the monolith becomes complex to deal with. And that's because everything is inside it. So your storage, I need more storage, but actually I don't need too much computational power because I just insert a lot, but I never read that data. While you still have to run a multi-master Postgres, so you need actually to manage multiple nodes at once. Or my queries are very complex, but once they execute, they are fairly easy to run because they can be distributed to multiple nodes. So my bottleneck is actually the SQL parser optimizer. And in that case, I cannot scale just the query planner, for example. Or at least all those things were possible, but they required a lot of knowledge, expertise, and complexity involved. And frequently, you have to re-engineer things. Like when you move to a sharded environment, you start having the need to move some logic inside your own application to understand proper routing of the queries, eventually consistency between the shards or things like that. When you involve replication, you need to account for the replication latency if you actually want to be able to read from multiple nodes. And all those kind of things that require actually re-engineering your solution, not just a DevOps problem. And especially the part that I always loved the most in working with database system for years was that touching any problem could have a totally different effect. Touching any configuration parameter could have a totally different effect depending on the exact kind of query you were trying to run. So it was a very hard problem that depended on the hardware you were targeting, but also your exact workload you were targeting. So configuring something like Postgres, more or less more similar to magic than actual science, even though you can have, like, there are formulas that allow you to put those variables in a decent relation, but it's still like, if the user is going to generate to cause the wrong query, I'm still going to have problems even though I set everything in the most reasonable way. And that's how the concept of composable data system was born. Or better, it's something that was already there, but we never gave it an official name. And we never have been able to agree more or less on how to build composable data system during the course of years. And the foundations are, as I told you, the fact that you have specialized components. So all the things we have seen here, storage, execution engine, query planner, concurrency control, or every other component you can think of, is not something that is built into your technology. It's just a piece that you can pick and use in your system. And by virtue of that design, it's much easier to tune, replace, or scale your component. For example, if I'm able to combine different compute engines, I could use two compute engines, one near the other, that assess the same exact data. And by assess the same exact data, I'm not talking about assessing the same database, because the database is not data. The database implies accessing to the data, converting it to a format that the database understands, converting it to a format that your network transmission understands, and converting it to a format that your application understands. So because Python does not speak Postgres binary network protocol, and Postgres in memory, I never checked, but I would bet that it does not store the data the same exact way it ships them via network. So in this case, instead, you actually are able to access the same exact original file and data with different compute engines. So for example, I could have a query planner that parts of my query ships it to the engine optimized for analytics. Maybe you have a super vertical engine that only has to run group by count or something like that. And you have a totally separate engine that only has to do linear regressions, okay, for inference. And the two have different optimizations involved and could be provided by two different engines optimized for those use cases. And to allow those components to work together, they need to speak the same language. And that's why the composable data systems are by definition based on open source interface and formats. Formats like Arrow, Substrate, Parquet, Iceberg, or other similar solutions that allow you to share the same language for your data, same language for your queries, and allow your query planner to speak the same exact language that the engine speaks, so that when the query planner has to forward the query to the right engine, it does not have to translate the query. It's already in the format that the engine itself understands. And they must avoid vendor lock-in or technology lock-in. If I start with one technology, I should be able to replace that component with any other component that speaks those same standards and languages. Which means that if you are not happy with the invoices you receive by your provider, you can change it. So more or less, this is the architecture of a very high-level data platform. And you see that we have a few questions that your architecture has to answer generally, which is, how do I express my analysis, my query interface? How do I explain the analysis I actually want to do to my compute engine, so my intermediate representation? Or how do those analyses actually get sent to the compute engine itself? Or how does the compute engine read the data? Where does the data come from? What's the format of this data? What does my compute engine understand? And once you read that data, how does it keep it in memory? All those questions are more or less answered by a separate component that I try to surface here by the different blocks. And now, during the course of the talk, we are going to see what are the most commonly available options for each one of those components, starting from things like your query interface. The query interface is simply how you express the analysis that you want to run against your system. And in Python, R, SQL, or Spark ecosystem, there are tons of ways you can do that. And one good thing is that they are trying to converge. They finally understood that having too many solutions to do the same thing is a good thing, as far as they are able to speak to more or less the same ecosystem. So we have started seeing solutions like IBIS in Python that try to abstract when you have to access a data frame library, which is a form of compute engine in the end, or a SQL database. In both cases, you work via IBIS. Then Narvas tried to say, okay, but actually for most use cases, you need to abstract the data frame library, so I will focus more or less only on data frame libraries. Even though now, obviously, they are starting to build support for the other side of things. And on the R world, there were solutions like dplyr and dbplyr. We tried to do the same exact thing. Or we had SQL Alchemy for years that tried to abstract this database we are trying to interface to. So we tried to build abstraction that solved the problem of the fact that all these target systems spoke different languages. But one of the answers could have been just to agree on intermediate representation for the analysis I wanted to express. And that's the reason why Substrate was created. Substrate is that intermediate representation that marshals, that dumps in a format that your compute engine can understand, the query itself, the analysis you are trying to run. And it's a format designed to be easy to produce for the libraries that have to build it, but also easy to understand for the compute engine. What does it mean? It means that it is a bit in between a logical and physical query plan. So the logical query plan is how you as a human thought about your queries. Okay, you say, I want to add two numbers, two columns. Okay, but you don't have to go into the detail of saying, okay, the two columns are float columns, so I actually need to use this exact implementation of add. You just write add. But that add for the compute engine actually translates to 5, 6 different functions that it has to dispatch based on the types of the columns involved in the operation. So you express your logical plan, but then the compute engine has to parse that logical plan into a physical plan and say, okay, he wants to run a hard operation, and the two columns, the two identifiers that they provided are actually float columns, so I need to translate the plan to actually invoke the specific add version instead of just add. So Substrate tries to balance between the two worlds. So it has explicit about the schema. So the client that generates the query has to know the schema that it's targeting, and the schema has to be passed as part of your Substrate query. So the engine knows that you are trying to target a float column and does not have to resolve the schema itself before it can run the query. They all agree on the types that we are working with. And then I can talk with any engine that supports Substrate. And there are already a few of them, actually. So let's take a look at Substrate. We know that this is more or less the list of engines or technologies that already have support for Substrate at different levels. I would consider Substrate still an experimental technology. It's one of those standards that is a very good idea. It works in practice, but we don't yet know if in 10 years it will be what everyone agrees on. But there are some engines that already agreed that it makes sense to experiment with it, try it, and see if it sticks on long term. So we have DuckDB, we have Acero, which is the compute engine in Arrow itself. We have Data Fusion, we have Gluten, we have the legacy implementation of Velox. I think they are now separating Substrate as a separate component of the engine. We have Ibris, which is able to produce Substrate. We have dplyr Substrate, which is able to produce Substrate for your dplyr expression. And we have protocols like FlySQL ADPC that support Substrate natively. And this is more or less how a Substrate plan works. It looks like. So you see that it's very verbose because it's not written for us humans. It's written for computers. So you still are going to write your queries in SQL, probably. You don't have to learn a new language just to run your group by count. So, but the difference is that your client will now translate your group by count into a Substrate plan and ship the Substrate plan to the engine instead of the SQL string itself. And as you see, it's more or less verbose about the types too. It tells me, okay, I'm working on an underlying schema that is made of two columns, first name and surname, which are strings and could be nullable. And actually, out of this schema, I only want to read the people. No, the people is the table, the first name column. So that's the corresponding SQL query. And you see that it's like a super short query actually turns into a fairly big Substrate plan. But the plan is not expressed in this syntax, in the sense that this is the human version of the plan. The plan itself is actually protobuf binary data. So you're never going to read Substrate as a human. It's just binary data that gets shipped through the network. But one very interesting part of Substrate is that it is designed to be decomposable, which means that for any part of the Substrate query, as it is a tree, I could extract a subtree and ship only that piece to another component or layer under me. So an engine that actually has, like the example we did before, I integrate two different engines. The planner could take one part of the query, extract it from the substrate tree, send it to the inference engine, and then replace in the original query the outcome of that execution and send the remaining part to the analytics engine, which will be able to do further analysis on top of the data that was already returned by the inference engine. When I say this app is not meant for humans, I say for real, because this is a simple group by count. Okay, so don't try to do that. Use something that generates substrate for you. So the next step we have is connectivity. Now that I'm able to represent my queries, how do I actually send those queries to the engine that I want to reach? And that's why technologies like Flight, and on top of Flight, FlySQL, and on top of FlySQL and other drivers, ADBC was invented. They are more or less the equivalent of what it is ODBC or JDBC, but for column measure data, okay, for data for analytics systems primarily. And they are much more lightweight protocols that don't involve all the communication overhead that you have in like managing the cursor that typically the other protocols involve. You don't have all that back and forth with your database. So it's more or less designed to be as fast as possible at transferring data that is by design column major. What are those protocols? So you can see them like a stack. At the lowest point, we have Flight. Flight is no more than a framework to transfer data. So the only thing that it understands at its foundation is the concept of a column in practice, or a set of columns, and that it has to be sent to someone. And how those columns are sent. They are sent in a standard format so that everyone that understands Flight is able to speak with a Flight server or client. But it has limited capability in terms of everything else, in terms of coordination, control of the transmission, even though it can be extended via custom actions. And an extension on top of Flight that adds custom actions specifically designed for queries is FlySQL. So FlySQL is an extension of Flight that builds a protocol designed to send SQL or substrate queries and receive data via Flight. And on top of that, we can have ADBC, which actually does not limited force to work with FlySQL. ADBC is able to work with other protocols too. But it is your abstraction. It's probably going to be the library you're going to use. You're not going to talk Flight directly. And you just point your ADBC driver to whatever storage you have, and it's up to the ADBC driver to do the right thing. The only thing you know that if you are using ADBC, all your results will be transferred in a specific format that is the arrow format, and that any driver that implements ADBC is going to return you the results on column major format. And why does it matter? You might say, okay, now I have arrows and arrow fly, but why does it matter? Why should I care? Well, this is the reason in practice, okay? So this is the time it takes to transfer the same amount of data in different types over those three technologies, or those three libraries. So PyMySQL, Pandas, Read SQL, and Arrow Flight. And honestly, it's fairly easy to see how long it takes with Pandas and PyMySQL. It's not as easy to see how long it takes when you use Flight. So we are talking about not a small improvement. We are talking about a major change of paradigm in terms of how much data you can actually exchange between those components. And one of the recently Apache Druid has switched to Flight. And this is actually a graph out of the Apache Druid benchmark suite that shows you how much improved for them to return the results out of the Druid database to the client. And as we said, we have to agree on a format that can go through Fly. And what's this format? It's what you already heard me mention it a few times, but it is Apache Arrow. Apache Arrow is a format designed to represent data in a binary format. So it's not something like JSON. It's pure binary. And that it is designed to avoid this exact problem. When you had to speak, to collaborate between different components, before, each one of those had to read the data and convert it into something else that we're able to work with. For example, in the past, because now they are converging to Arrow, so things are not like that anymore. But in the past, there were cases where if you had XGBoost and you wanted to run your boosted tree on a pandas data frame, XGBoost actually had to decode the pandas data frame into NumPy, purely NumPy data, because yes, pandas used NumPy as its foundation, but the layout of the data is not as simple as one might expect. It tries to use multidimensional data as much as possible. But it had to perform some form of conversion unless they were just simple numeric columns. And that conversion had a cost, just to be able to run a different library on your data frame. Now that they agree on Arrow, that cost is gone. Like, each one of them can read the data that the other one produced. And they don't even care about who produced that data. I don't have to implement my conversion for pandas itself. I can just access the underlying data, the same data that pandas already has in memory, so I don't have to read it from anywhere. It's already there in my memory. Imagine it's just a pointer. I point to the same exact memory area, and I work on top of it, as if it was my own memory. And this works, and has two different side effects that are very interesting. First of all, it's very fast. Like, up to the point that this is an example that I really like, because it shows that if I have a dictionary on NumPy arrays, building a data frame in pandas out of that dictionary NumPy array involves a cost that is actually higher than building a PyArrow table, an arrow table from those arrays, and then converting the table to pandas. So doing two steps via the Arrow format, it's actually faster than doing only one step from NumPy to pandas directly. And this is changing, more or less. I didn't try, like, now, the example. And pandas is slowly moving to Arrow internally. It already uses Arrow for string columns. And there are ongoing discussions about extending the support to other column types, too. But like all widely adopted technologies by pandas, those discussions are not easy, are taking time, has been going on for, I think, more than a year, maybe 2 years, something like that. But eventually, we will get there probably at one point, one way or another. And the other very interesting part, side effect of the idea of using a standard format, is that if you ever worked with a diverse set of data engineers and data analysts, you might have heard of R, which is another programming language that people that come from science really love. And as engineers instead really love Python, but sometimes we have to work together. And if we both speak Arrow, we can exchange the data between the two. And like a Python program can invoke an R function at 0 cost. So when I mean exchange data, I don't mean that you convert the data to the R memory format or anything like that. I mean that you just pass the pointer to that data to the R language, and the R language knows that it's an arrow array, and it will create an arrow equivalent class on the R side without copying or converting any data. So your function has actually no other cost than the function call itself, as if we were calling another R function, not much different. And in Python, this is implemented via the PyCapsule protocol, the arrow PyCapsule protocol, because the generic PyCapsule protocol is the different thing. But the arrow PyCapsule protocol, in practice, allows every Python library to receive and exchange arrow data without having to care about that underlying machinery of passing pointers and things like that. So, what do compute engine do in this context? Well, when I have an arrow-based compute engine, there are some major benefits that I get by a consequence of all the layers we discussed before speaking arrow. So an arrow compute engine means that it's a compute engine that uses arrow to send back the result to me, to my client, and uses arrow itself as its in-memory format. Why this is important? It's important because when I read the data, I perform, imagine a filter. Okay, what your compute engine can do is take all the rows that do actually are lower than 5, okay? So in reality, in the arrow format, the rows are a continuous array of memory. And if I don't have to perform any conversion, I can just get the pointer to the end of my list of rows and say, okay, this is where the last row is. After this, they are all columns, rows bigger than 5, okay? And I just have to pass to the network layer the starting pointer and say, take data up to this pointer. And I don't have to do any marshalling to send it via the network or any other change, because arrow itself is a standard, and anyone who receives the data in the arrow format, it's going to be able to read it. So this is something that's already implemented by some engines like Data Fusion, DB, Polars, and Velox. And one benefit if you work with some modern technologies is that frequently your network controller is able to directly read from the memory. So even at the hardware level, you don't really have to do any copy. And by using arrow, all this complexity, which is more or less the data-related software and libraries from 2023, so it probably works now, could be put under control. And at the end of the chain, I have my data storage, which is what the compute engine has to access. And the same way it said for the previous layer applies here. In my data storage speaks arrow and substrate, I'm able to access the data independently from where it is, and I don't have to care if I change my data storage, if I move from S3 to another flight source, so another compute engine, or I connect to Snowflake via IDBC, it does not matter. They all speak arrow. And if my my storage format understands substrate, I'm even able to extract part of the substrate pen and push down projections and filters, for example. Like the people in Min.io at a certain point discussed the idea of having the storage layer itself, something like S3 select, that speaks substrate, so that I could select only the files that already match the predicate and avoid transferring all the data. There are some data formats that already arrow native or arrow compatible. So like, for example, the LANS format and the arrow IPC format are arrow native, which means that, for example, if I read the data from those formats, it's zero copy. I can do frequently in the case of LANS and always in the case of arrow, just memory map the data from my disk. And that's all. The library does not have to perform any conversion. For more complex formats like Parquet, Iceberg, some kind of decoding has to happen. While they are compressed format, dictionary encoded, runland encoded, all those things have to be decompressed. But there are fast implementation of those paths. So they are compatible enough with the memory format of Arrow that the decoding is minimal, not zero, but it's reduced compared to converting them to something else. Obviously, if you read your data from CSV or JSON, that has totally to be converted to Arrow. So being able to use a composable system does also mean that it's scalable and fast, because I can replace my components. So for example, if I have here, it's a comparison between a query on Spark that takes on 10 terabytes of data a certain amount of time based on the amount of nodes. And if I could replace the Spark execution engine with a GPU-based engine, in many cases, this is the comparison of how much time it will take to run the same exact query. And if I use Arrow and Substrate, I don't have to touch anything else. Throw away your compute engine, replace it with QDF, and that's what you get. So this is the benefit of composable solution. Not only my developers can work in their favorite language and then don't have to learn specific technologies, but I can replace all those pieces based on the one that performs better in my scale or my complexity. And how that's possible? Because it's arrows all the way down. And if you are wondering how complex it is to actually build a data platform on top of those technologies, this is a very bad and ugly example of what you could do, and by involving PyArrow, by involving IBIS, Substrate, and Arrow itself, and Acero, which is the compute engine of Arrow itself, I can build a SQL database in 50 lines of code, or something like that if you consider the import. And it works. Like I can just pass the SQL query in command line. It will read the data from the Parquet file that is named the same as your table and perform the analytics you asked for. That's it. I hope I gave you a more or less good understanding of how composable datasets are, what they are. If you are interested, I tried to write in the past a little project, which is Data Playground, which builds an entire computation analytics platform from scratch, up to building the compute engine itself, in a very simplified way, whose only purpose is to explain the main concept to people that want to understand more or less how a system like that works. And if you want to keep up with the news on those technologies, you can subscribe to the monthly Python Data Engineering newsletter, where I talk about all the new releases of those technologies and the cool features they implement. So I hope you will at least start experimenting with more composable solutions based on Arrow and Substrate. And if you have questions, you can find me at the PyDrinks, or now. Exactly.
All right. Thank you, Alessandro. We have plenty of questions. I don't think we have enough time to go through all over these questions. So I'm going to ask you the first one. It's a long one. Composable systems allow to have things divided by responsibilities and enable to scale parts without affecting others. But now you have dozens of small pieces to connect and test to make sure it works. How do you see this trade-off?
Well, it's a very good question, actually. And I believe that it's a question that it's interesting because the fact that the system is composable does not mean that you have to compose it yourself. So you can take something like DuckDB, and it's ready to use. It does just read SQL for you. It just does execute the queries on Parquet files for you. In between, it has its own network connectivity implemented, its own compute engine implemented, and it's actually very good. It performs very well. It's effective, and it's built on those technologies. So if you tomorrow wants to move from DuckDB to something else, you can. You're not stuck there, but you can start from something simple and self-contained like DuckDB.
Thank you. Second one. Many open source tools are built by companies trying to make money. How can they be convinced to implement standards which avoid lock-in when they might risk them losing customers?
Oh, that's interesting. From one point of view, let me tell you that many of those technologies, exactly because we see their value at a scale, like for the world computer science, they are managed by foundations or things like that. So that's why you frequently see the name Apache in front of those technologies, because they wanted to go behind the foundation that gives rules and guarantees that decisions are not made by a single company. So it's not going to be there a company that decides everything for you and you must apply. There are a lot of companies, some of them big, like Intel, Microsoft, or people like that, that are involved in our development, but they cannot make decisions by themselves. They have to agree with each other, and by virtue of that, no one of them is cut out of the decision process. So they actually benefit from the fact that they have a technology that integrates with the other technologies, and that allows them to pull people into their solution if it has a value. It's true they can no longer use vendor lock-in as a way to force people to stay there, but as far as their solution is able to provide value, they can attract people that are in the same ecosystem.
Thanks. Now let's open the Pandora vase. Can you explain why Arrow is so fundamentally faster?
Okay. There are a few reasons. First of all, Arrow is designed for its job in the sense that the way the data is represented in memory is as much as possible close to how your computer wants it to be. It's contiguous, memory aligned, it's in the same format your compute engine usually expects, and it's fast because of that, because it allows the compute engine to implement vectorized execution on top of that data. And it's fast because it allows the compute engine and all the other nodes involved to exchange that data without having to copy it. When you have seen that graph of how fast it is for SQL compared to the other protocol, yes, part of that is because Arrow is very lightweight, it's easy to transfer for the machine. But part for that, it's also because we are skipping many copies at all levels. We are skipping the moment the compute engine has to encode that data to go to the network. We are skipping the moment where the network has to copy it to send it through the line because it can use DMA by virtue of the fact that the data is not to be re-encoded. We are skipping the decoding phase on the side that actually received that data. And same as before, we can actually perform direct memory access to read that data because it has not to be translated or decoded. All these decoding steps allow your computer to go through optimized paths that don't involve the CPU at all to be performed. And that's why it becomes faster.
Great. Keep going. Zero copy conversion is nice, but how does it compare with keeping everything native to the original engine, now was IBIS, without changing the API? Is that clear? Should I repeat it?
Yeah, maybe.
Okay,
yes.
so zero copy
conversion
is nice. That's a statement.
Yeah.
But how does it compare with keeping everything native to the original engine without changing the API? And then the question is mentioned IBIS as an example.
Yeah, okay. Well, you can. I mean, you're not forced to change the API. As I said before, you can use things like Snowflake speaks Arrow and speaks SQL. DuckDB speaks Arrow and speaks SQL. They are more or less solutions that allow you to stick to the same API. If you use Polars, okay? How many people here use Polars? I bet there are quite a few. Great. So polars are arrow-based. So you can keep using polars and also integrate it with other arrow libraries, arrow-based libraries. As far as your library speaks arrow, you can use it with polars. Now PySpark just released like a day or two ago, I don't remember, a simple new method that your data frame I have, which is 2arrow, which exposes the Spark results as a plain arrow table. So I could, in theory, perform a query on Spark, get it as an arrow table, and run a further analysis via polars on top of it, without any conversion cost in the way. So the fact that it's composable means that you can pick the components you want when you want. You are not forced to replace your entire stack.
Okay, thank you. I think we have time for a couple of questions. Do you see support for large cloud providers towards composable data systems, or do you see obstacles in adopting this approach?
It depends. Let me answer it that way, in the sense that it depends what you will be looking for from your provider. There are providers that work at a more foundational level that are probably considering or already adopting some of those technologies. I give you the example of Min.io. Like, it makes total sense for them to evaluate the use of a standard like Substrate for the queries, because it allowed them to be integrated in this composable ecosystem in an easy way. But other solutions, like other providers like Snowflake or Databricks, they probably want to be able to interact with that composable system, but internally, you really don't know how deep that those technologies are involved. They could perfectly have, for whatever technical reason that makes total sense in that context, have a totally different memory format. But in the end, as far as I, as a user, receive arrow data, I can still involve all those technologies that we talked about before and build my solution. And if in the future I switch from that database cloud system to something else, my code has not to change because it still speaks ADBC and still speaks arrow.
Okay, time for the last question now. How does Substrate handle complex type which might be different between languages or technologies? For example, in Python we have datetime, but in SQLite we represent them as strings.
Okay, they have a standard representation for those. So Substrate, for many of those types, tells you you have to encode it this exact way. So there is a defined Marshall format for those types. When you have to pass constants, okay, the types themselves at the data level are managed by arrow, okay. At the constants level, they could be managed by Substrate instead. And for other formats, Substrate is designed to allow extensions. Extension both for functionalities, so additional functions that your system might implement, add some, whatever, and types, so float balls, whatever, okay? You can define them and inject in your Substrate query where the definition of those extensions is available for fetch, and your compute engine will fetch the definition from that place and will be able to understand the types you wrote in your query.
Okay, thank you again, Alessandro.
Thank you.
Just one note here. If you are joining PyDrinks, be sure that you have your QR code ticket handy and just present that at the entrance. And at 7:40 at the PyDrinks, of course, there will be a challenge between these conference organizers. I don't know what it is. It's going to be a surprise. No, I'm not kidding. That's true. So if you are there, you're going to enjoy this fun time among us. So thank you.